Close your eyes for a second. Imagine you are standing in the Mesopotamian desert, roughly 5,000 years ago. No city lights, no polyution, no phone screen burning your retinas at 2 in the morning. Just you, the sand, and a sky so thick with stars it almost looks fake. You look up, and you see thousands of white pinpricks, and you think what every human being thought for millennia. Those are gods. Those are decorations. Those are anything except what they actually are. The Babylonians were the first to get serious about tracking those lights. They carved star catalogs into clay tablets, mapped the movements of the planets they could see with the naked eye, and built an entire religious framework around the idea that celestial bodies controlled human fate. Mercury, Venus, Mars, Jupiter, Saturn. 5 wandering lights against a fixed backdrop. They called them wild sheep because they moved on their own, which, honestly, is a more poetic name than anything we have come up with since. But here is what the Babylonians never asked. What were those wandering lights made of? What happened if you could actually go there? They tracked positions and predicted eclipses with terrifying accuracy. But the physical nature of the planets? That was not a question their framework could even process. The sky was divine. The stars were messages. And the idea that those points of light might be real, physical places with surfaces you could stand on, that would take another 2,000 years to even enter the conversation. Enter the Greeks. And look, saying the Greeks is doing a lot of heavy lifting because Greek philosophy was not one unified thing. It was dozens of competing schools screaming at each other across the Mediterranean for centuries. But in the 5th century BCE, a man named Leucippus and his student Democritus proposed something genuinely radical. They said everything in the universe, including the stars, was made of tiny, indivisible particles called atoms. And if atoms were infinite, and the void was infinite, then the number of worlds out there must also be infinite. Think about that for a moment. 2,500 years ago, a Greek philosopher looked at the sky and said there must be countless other worlds out there, some with life, some barren, some completely unlike anything we have ever seen. He did not have a telescope. He did not have math beyond basic geometry. He just followed the logic of infinite matter and infinite space and arrived at a conclusion that modern astronomy is still confirming today. Democritus was right, and nobody listened. They did not listen because Aristotle showed up. And when Aristotle showed up, everybody else might as well have gone home. Aristotle declared that Earth was the center of everything, that the celestial spheres were perfect and unchanging, and that the idea of multiple worlds was logically impossible. One Earth, one cosmos. Everything else revolves around us. It was elegant, it was wrong, and it dominated Western thought for nearly 2,000 years. 2 millennia of intellectual paralysis because one very confident man said no. Now, to be fair to Aristotle, and I do not particularly want to be fair to Aristotle on this point, he was working within the observational limits of his time. The stars did not appear to move relative to each other, so assuming they were fixed on a distant sphere was not insane. The Earth did not feel like it was moving, so putting it at the center seemed reasonable. But the damage his authority did to the question of other worlds is hard to overstate. For centuries, even thinking about planets around other stars was not just wrong. It was unthinkable. Fast forward to 1543. A Polish mathematician named Nicholas Copernicus, lying on his deathbed, finally publishes a book he has been sitting on for decades, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. In it, he quietly, politely, almost apologetically suggests that the Earth is not the center of the universe. The Sun is, and the Earth, along with the other known planets, orbits around it. He published it while dying, probably because he knew what would happen if he published it while healthy. Copernicus was careful. He framed his model as a mathematical convenience, not necessarily physical truth. He dedicated the book to the Pope. He did everything he could to avoid the firestorm. And for a while it worked. The church mostly ignored the book because most people could not understand it, and the ones who were too busy arguing about the math to notice the theological dynamite buried underneath. But the fuse was lit. If Earth was not special, if it was just another planet orbiting a star, then what were all those other stars? Galileo Galilei picked up that fuse in 1609 when he pointed a telescope at Jupiter and saw 4 tiny moons orbiting it. Io, Europa, Ganymede, Callisto. For worlds circling another planet, not Earth. This was direct, visual, undeniable proof that not everything in the sky revolved around us. The Aristotelian model cracked in real time. Galileo published his findings. The church told him to shut up, and he famously did not shut up. It cost him his freedom. He spent the last 9 years of his life under house arrest. But Galileo got off easy compared to the man who came before him. Giordano Bruno. This is where the story gets dark, and it stays dark for a while. Bruno was an Italian friar, philosopher, mathematician, and poet who took Copernicus's heliocentric model and ran with it so far that he left the known universe entirely. Bruno did not just say the Earth orbits the sun. He said the sun is a star. He said the stars are other suns. And he said those other suns have their own planets with their own life. Let that sink in. In the 1580s, a former Dominican friar was traveling across Europe telling anyone who would listen that the universe is infinite, that it contains countless worlds, and that life exists beyond Earth. This was not a safe thing to say in the 16th century. This was not even a remotely survivable thing to say. The Catholic Church had a very specific way of dealing with ideas that threatened its cosmological authority, and that way involved chains, dungeons, and fire. In 1592, Bruno was arrested by the Venetian Inquisition and handed over to the Roman Inquisition. He spent 8 years in prison. 8 years. They interrogated him, demanded he recant his cosmological views, and he refused. Again and again and again. The trial records are incomplete, but what survives makes it clear that Bruno's belief in multiple worlds was a central charge against him. Not the only charge, but one of the most prominent. He would not bend. On February 17, 1600, Giordano Bruno was led to the Campo de' Fiori in Rome, stripped naked, tied to a wooden stake, and burned alive. According to one account, they drove an iron spike through his tongue so he could not speak to the crowd during his execution. He was 51 years old. The crime, in essence, was imagining that other planets existed. The universe he described, infinite and teeming with worlds, turned out to be the one we actually live in. It just took 400 more years to prove it. There's a bronze statue of Bruno standing in the Campo de' Fiori today, right where they killed him. His hood is up, his face is shadowed, and he stares straight ahead with the kind of expression that says, "I told you so," louder than any inscription ever could. Every February, people lay flowers at his feet. The irony is almost too thick to bear. The man was executed for saying what every astronomy textbook now teaches in the first chapter. After Bruno, the question of other worlds went underground for a while. Not because people stopped thinking about it, but because people stopped saying it out loud. Galileo's house arrest in 1633 reinforced the message. Challenge the church's cosmology and pay the price. But the scientific revolution could not be stopped by burning one man. Johannes Kepler described the laws of planetary motion. Isaac Newton explained gravity. And slowly, painfully, the scaffolding of the old geocentric universe collapsed piece by piece. By the 18th century, the idea that stars were other suns was widely accepted among astronomers. William Herschel, the man who discovered Uranus in 1781, openly speculated about life on other planets, including the moon and even the sun itself. He was wrong about the sun, obviously, but the point is that the conversation had shifted. Other worlds were no longer heresy. They were hypotheses. The question was no longer whether other planets existed. The question was what they looked like. And that question, what other planets might actually look like, haunted astronomy for the next 200 years. Because there was a terrifying gap between believing other worlds existed and actually being able to see one. Stars were so far away that even the best telescopes of the 19th and 20th centuries could not resolve planets around them. The light of a star drowns out everything nearby. Trying to see an exoplanet with a telescope was like trying to spot a firefly next to a searchlight from 1,000 miles away. So for centuries, other planets remained theoretical. Scientists knew they should exist. The math said they should exist. Logic said they should exist. But nobody could find one. And in that silence, in that gap between certainty and evidence, the imagination had room to run wild. Science fiction filled the void with everything from paradise worlds to hostile alien empires. The real question nobody wanted to ask was simpler and uglier. What if the actual planets out there are worse than anything we imagined? Because here's the thing about human imagination. We tend to project ourselves outward. We imagine other worlds as variations of Earth, places with oceans and mountains and breathable air, maybe a different color sky, maybe 2 moons instead of 1. We imagine worlds we could visit, worlds we could colonize, worlds that make sense to us. The universe, as it turns out, has no obligation to make sense to us. And when we finally developed the technology to find real exoplanets, what we found was not a garden. It was a gallery of horrors. That story, the story of what we actually found when we finally looked, begins in the early 1990s. But before we get there, we need to reckon with something embarrassing. Before we started cataloging the nightmares orbiting distant stars, we had nightmares orbiting our own. Planets and moons so hostile, so violent, so fundamentally alien that they should have warned us about what was coming. We just were not paying close enough attention. Let's talk about Venus, because Venus might be the greatest bait and switch in the entire solar system. From Earth, Venus is the brightest object in the sky after the sun and moon. Ancient Romans named it after their goddess of love and beauty. It is roughly the same size as Earth, roughly the same mass, roughly the same distance from the sun. If you were designing a twin planet on paper, you would end up with something very close to Venus. And then you would visit it and immediately regret every decision that led you there. The surface temperature of Venus is around 900 degrees Fahrenheit. That is hotter than Mercury, which is literally closer to the sun. How? Because Venus has an atmosphere made almost entirely of carbon dioxide, and it is 90 times thicker than Earth's atmosphere. 90 times. Standing on the surface of Venus would feel like being a kilometer underwater, except instead of water, you're surrounded by superheated toxic gas. The pressure alone would crush a human body like a soda can under a truck tire. And then there are the clouds. Venus has 3 layers of clouds made primarily of sulfuric acid, not water vapor. Sulfuric acid, the same substance that dissolves metal, burns through organic tissue, and is used in industrial drain cleaners. It rains sulfuric acid on Venus, although the rain never reaches the surface because the lower atmosphere is so hot that the droplets evaporate before they land. So it rains acid that evaporates in midair. Even the weather on Venus is designed to hurt you in ways you did not think weather could. The Soviet Union tried to land on Venus multiple times. The Venera program sent a series of probes to the surface starting in the 1970s, and the results were, to put it kindly, humbling. Venera 7 landed in 1970 and transmitted data for about 23 minutes before the heat killed it. Venera 9 sent back the first photograph from the surface of another planet in 1975, a grainy black and white image of flat rocks under an orange sky. The probe lasted 53 minutes. No spacecraft has ever survived longer than about 2 hours on Venus. The planet simply does not allow visitors. Here is what makes Venus genuinely disturbing, though. Scientists believe Venus was once habitable. Models suggest it may have had liquid water oceans for billions of years, a mild temperature, a reasonable atmosphere, something like Earth. And then runaway greenhouse gases turned it into the screaming hellscape it is today. Venus is not just a hostile planet. It is a cautionary tale. It is what happens when a planet like ours goes wrong. and it is literally right next door. But Venus is at least solid. You can, theoretically, stand on it for the 2 minutes before you are simultaneously crushed, burned, and dissolved. Jupiter does not even give you that courtesy. Jupiter is a gas giant with no solid surface at all. If you try to land on Jupiter, you would simply fall down through layers of hydrogen and helium gas that get progressively denser and hotter until thousands of miles below the cloud tops. The pressure compresses hydrogen into a liquid metal. You would be crushed long before you got there, but the principle is unsettling. Jupiter's Great Red Spot is a storm larger than the entire Earth, and it has been raging for at least 350 years. Winds at its edges reach 400 miles per hour. The storm is so large that you could drop 3 Earths into it side by side and still have room left over. And it is not the only storm. Jupiter is covered in bands of competing jet streams, cyclones, and anticyclones that tear through the upper atmosphere in a constant, churning chaos that makes the worst hurricane on Earth look like a light breeze. But the real killer on Jupiter is not the storms. It is the radiation. Jupiter has the strongest magnetic field of any planet in the solar system, and that field traps charged particles from the solar wind into radiation belts so intense that they would deliver a lethal dose to an unshielded human in minutes. Not hours, minutes. The Juno spacecraft, which has been orbiting Jupiter since 2016, has its electronics housed in a titanium vault specifically to survive the radiation. Even inside that vault, the instruments are slowly being degraded. Jupiter does not just kill you, it irradiates your corpse. And then there is Io, Jupiter's innermost large moon, and arguably the most volcanically active body in the entire solar system. Io is caught in a gravitational tug of war between Jupiter and the other Galilean moons, and the tidal forces squeeze and stretch its interior so violently that the entire moon is essentially being kneaded like dough. The result is hundreds of active volcanoes, some of which shoot plumes of sulfur dioxide over 300 miles into space. The surface of Io is a patchwork of yellows, reds, oranges, and blacks. It looks like a pizza designed by someone who hates you. Io's volcanoes resurface the entire moon so frequently that there are almost no impact craters visible. Think about what that means. In a solar system where every solid body is pockmarked with craters from billions of years of bombardment, Io is so volcanically active that it erases the evidence faster than the universe can leave it. The surface temperature near active vents can reach 3,000 degrees Fahrenheit. Lakes of liquid lava sit in calderas kilometers wide, and the thin atmosphere is made almost entirely of sulfur dioxide, which is about as breathable as car exhaust. Move outward to Europa, and the horror shifts from fire to ice. Europa is covered in a smooth shell of water ice, crisscrossed with reddish-brown streaks that scientists believe are deposits of salts and sulfur compounds from below. Beneath that ice shell, there's almost certainly a liquid water ocean, kept warm by the same tidal heating that tortures Io. The ocean may contain more water than all of Earth's oceans combined. It is one of the most promising places to look for extraterrestrial life. It is also buried under miles of ice in a radiation bath that would cook anything on the surface. Saturn's moon Titan offers a different kind of alien nightmare. Titan is the only moon in the solar system with a thick atmosphere, denser than Earth's actually, and it is the only place besides Earth where we have confirmed stable bodies of liquid on the surface. Except those lakes and rivers are not water. They are liquid methane and ethane. It rains hydrocarbons on Titan. The Huygens probe landed there in 2005 and photographed a landscape of rounded pebbles made of water ice, sitting on a frozen plain under an orange sky. Beautiful in a deeply unsettling way. The temperature on Titan's surface sits around minus 290 degrees Fahrenheit. At that temperature, water ice is hard as granite. Methane, which we know as natural gas on Earth, flows like water. The landscape has been shaped by methane rain carving channels and filling basins exactly the way water does on Earth, creating a hydrological cycle that is chemically alien but structurally familiar. Dunes made of organic molecules stretch across the equatorial regions. It is like looking at a dark, frozen mirror of Earth where every element has been swapped for something worse. And then there are the outer worlds, Uranus and Neptune, the ice giants. These two planets sit so far from the Sun that they receive almost no light and almost no heat. Uranus is tilted 98 degrees on its axis, essentially rolling around the Sun on its side. Nobody knows exactly why. The best theory involves a collision with an Earth-sized object billions of years ago that knocked it over. A planet got body-checked so hard it has been rolling sideways for 4 billion years. The universe has a cruel sense of humor. Inside Uranus and Neptune, conditions get genuinely science fiction. The atmospheres are hydrogen, helium, and methane, which gives both planets their distinctive blue and blue-green colors. But deeper inside, pressures and temperatures rise to extremes where the methane molecules get ripped apart and the carbon atoms are compressed so intensely that they crystallize into diamond. It rains diamonds inside Uranus and Neptune, actual diamonds, falling through atmospheres of crushing pressure and extreme heat, sinking toward cores we have never seen and may never see. Scientists at the SLAC National Accelerator Laboratory actually recreated these conditions in 2017. They used high-powered lasers to blast polystyrene, a stand-in for the methane-rich compounds in ice giant atmospheres, and watched as nanoscale diamonds formed under the extreme pressure. The experiment confirmed what models have been suggesting for decades. Diamond rain is real. It is happening right now on 2 planets in our own solar system, and we only confirmed it in the last few years. Our own backyard is stranger than we realized. Neptune also holds the record for the fastest winds in the solar system. Wind speeds on Neptune can reach 1,200 miles per hour. For context, the most powerful tornado ever recorded on Earth had winds around 300 miles per hour. Neptune quadruples that, and it does it in temperatures approaching minus 330 degrees Fahrenheit, in near total darkness, on a planet so far from the Sun that noon looks like deep twilight on Earth. It is a frozen, screaming, lightless wind tunnel made of methane and ice, and it is technically our neighbor. Pluto, though reclassified and technically no longer a planet, deserves a mention in this gallery of horrors for sheer bleakness alone. When New Horizons flew past in 2015, it photographed a world of nitrogen ice plains, mountains of water ice, and a thin atmosphere that was actively freezing and falling to the surface as the dwarf planet moved further from the Sun. Pluto's heart-shaped nitrogen glacier, Tombaugh Regio, is hauntingly beautiful. It is also a feature on a world where the temperature hovers around minus 390 degrees Fahrenheit, and the Sun is just a bright star in the sky. So that is our solar system, the one we grew up learning about in school, the one with the colorful diagrams and the friendly mnemonics for remembering planet order. Crushing pressure, acid rain, liquid methane, diamond precipitation, volcanic eruptions that shoot material into space, radiation belts that kill in minutes, and winds 4 times faster than anything Earth has ever produced. This is the neighborhood. These are the planets we can actually visit with spacecraft. And every single one of them, except Earth, is trying to kill you in a different creative way. What makes this relevant to our story is context. Everything we just described exists within a single, relatively calm, relatively stable solar system orbiting a relatively ordinary star in a relatively quiet part of the galaxy. If this is what normal looks like, imagine what abnormal looks like. Imagine what planets look like around stars that are not calm, not stable, not ordinary. Imagine what forms in the chaotic, violent, radiation-soaked environments that make up most of the galaxy. We did not have to imagine for long, because in 1992, someone found the first ones. Before we talk about what Alexander Woolsey found, we need to talk about what he was looking at. Because the object at the center of this story is, by itself, one of the most violent things in the known universe. PSRB 1257 plus 12 is a pulsar. And a pulsar is what you get when a massive star runs out of fuel, collapses under its own gravity, and explodes in a supernova so powerful it outshines entire galaxies for a few weeks. What is left behind, if anything survives at all, is a neutron star. The compressed core, the skeleton. A neutron star packs roughly 1.5 times the mass of our Sun into a sphere about 12 miles across. 12 miles. That is roughly the distance from one side of a mid-sized city to the other. The density is so extreme that a teaspoon of neutron star material would weigh about 6 billion tons on Earth. The gravity at the surface is about 2 billion times stronger than Earth's gravity. If you dropped a marshmallow onto a neutron star from a meter above the surface, it would hit with the force of a nuclear weapon. Neutron stars do not play around. A pulsar is a neutron star that spins rapidly. Some pulsars rotate hundreds of times per second. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. And if those beams happen to sweep across Earth's line of sight, we detect regular pulses of radio waves. Like a cosmic lighthouse, PSRB 1257 plus 12 pulses about 161 times per second. It is spinning so fast that its surface, if you can call it a surface, is moving at a significant fraction of the speed of light. This is the object that Wolzin was studying. This is the dead star. Alexander Wolzin was a Polish astronomer working at the Arecibo Observatory in Puerto Rico, the massive radio telescope built into a natural sinkhole in the jungle. In 1990, he was studying millisecond pulsars, looking for subtle timing variations in their radio pulses. Pulsars are incredibly precise clocks. If something is gravitationally tugging on a pulsar, its pulses arrive slightly early or slightly late in a predictable pattern. Wolzin noticed exactly the kind of pattern in PSR B1257 plus 12. Something was orbiting this dead star, something with mass. Working with Dale Frail, a Canadian astronomer at the National Radio Astronomy Observatory, Wolzin analyzed the timing data and in January 1992 published a paper announcing the detection of two planets orbiting PSR B1257 plus 12. A third, smaller planet was confirmed shortly after. These were the first confirmed exoplanets in history. Not around a nice, friendly, sun-like star. Not in a habitable zone. Around the spinning, irradiated corpse of a star that had already exploded. The first other worlds we ever found were zombie planets. The reaction from the scientific community was, to put it generously, complicated. On one hand, this was the discovery everyone had been waiting for. Proof that planets existed beyond our solar system. On the other hand, nobody expected the first exoplanets to be orbiting a pulsar. The whole point was supposed to be finding Earth-like planets around Sun-like stars. Finding them around a neutron star was like searching for life in the ocean and discovering it first in a nuclear reactor's cooling pool. Technically a success, but deeply unsettling. There was also skepticism, serious skepticism. Just 2 years earlier, a British team led by Andrew Lyne had announced the discovery of a planet around a different pulsar, PSR 1829-10. It was a huge deal, front-page news. And then Lyne found an error in his data reduction. He had failed to account for Earth's slightly elliptical orbit when processing the timing measurements. The planet vanished. Lyne stood up at a meeting of the American Astronomical Society in January 1992 and publicly retracted the discovery. It was one of the most painful moments in modern astronomy. So when Wolzin and Frail announced their pulsar planets at the exact same meeting, days after Lyne's retraction, the audience was understandably nervous. Here we go again, people thought. Another false alarm, another embarrassment. But Wolzin's data was different. He had accounted for every known source of error. His timing analysis was airtight. And crucially, the gravitational interactions between the two larger planets produced a detectable effect that independently confirmed their existence. This was not a mistake. This was real. The planets themselves are as alien as their origin story. PSRB 1257 plus 12b is the smallest, roughly twice the mass of our moon, orbiting the pulsar every 25 days. PSRB 1257 plus 12C and D are both several times the mass of Earth, orbiting every 66 and 98 days respectively. They sit close to the pulsar, bathe in intense radiation that would sterilize any surface and strip away any atmosphere as we understand it. These are not places where life could exist. These are places where the concept of a surface is debatable. The big question, the one that haunted astronomers after the announcement, was how? How did these planets get there? The supernova that created the pulsar should have destroyed anything nearby. The explosion releases more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. Any planets orbiting the original star should have been vaporized or at the very least flung out of the system entirely. So either these planets somehow survived the most violent explosion in nature, or they formed afterward from the wreckage. Both options are extraordinary. The leading theory is that the pulsar planets formed from a fallback disk, a ring of material that was ejected during the supernova but did not reach escape velocity and fell back toward the neutron star. Over time, this disk of debris, composed of heavy elements forged in the explosion itself, coalesced into planets. Think about that. These worlds are not made from the primordial gas and dust that forms normal planets. They are made from the guts of a dead star. They are built from supernova shrapnel. They are, in the most literal sense, born from destruction. Another theory, less favored but not impossible, suggests the planets might be the remnant cores of gas giants that were in orbit before the supernova and survived the blast. If they were far enough away, the explosion might have stripped their atmospheres and outer layers without destroying them entirely, leaving behind dense, irradiated rocks. Zombie planets in the truest sense. Survivors of an apocalypse, stripped down to their bones, still circling the grave of their sun. What life would look like on these worlds, if the word even applies, is a question that borders on absurd. The pulsar emits intense beams of X-rays and gamma rays with every rotation, 161 times per second. The planets are constantly bathed in this radiation. Any atmosphere would be ionized. Any surface would be sterilized. The sky, if you could somehow stand on one of these worlds, would be dominated by the pulsar itself, a tiny, impossibly dense point of light that flickers faster than a strobe lamp, painting the landscape in lethal radiation with every pulse. There is something deeply poetic and deeply disturbing about the fact that the first planets we ever found outside our solar system were orbiting a dead star. We spent centuries imagining other worlds as places of possibility, places where life might thrive, places that might look like home. And the first actual evidence pointed to something much darker. Planets born from violence, existing in violence, offering nothing to anything that might try to live on them. The universe answered our question about other worlds, and the answer was yes, but you will not like them. The discovery also raised a profound statistical question. If planets can form around pulsars, around the remnants of the most violent stellar deaths in nature, then planet formation is not a delicate process that requires perfect conditions. It is a robust, almost inevitable process that happens everywhere, even in environments that should make it impossible. If planets can form here, they can form anywhere. And that means the galaxy is not sprinkled with planets. It is saturated with them, drowning in them. Modern estimates suggest there are more planets than stars in the Milky Way. At least 100 billion planets, and possibly several hundred billion. That means there are more alien worlds in our galaxy alone than there are grains of sand on every beach in every country on Earth. Some of them will be rocky, some will be gaseous, some will be frozen, some will be burning, and some, as we were about to discover, will be so bizarre, so extreme, and so fundamentally wrong by every standard we had that finding them would force us to throw out our models and start over from scratch. But in 1992, all of that was still ahead. The pulsar planets were a curiosity, an anomaly, something to marvel at and then set aside while the real search continued. The real search, the one everybody actually cared about, was for planets around normal, living, sun-like stars. Planets that might actually tell us something about our own origins. Planets that might be hospitable to life. That search was about to deliver its first result, and it was going to make the pulsar planets look calm by comparison. October 6th, 1995. A conference room in Florence, Italy. Michel Mayer, a Swiss astronomer from the University of Geneva, stands in front of a room full of his peers and announces that he and his graduate student, Didier Queloz, have found a planet orbiting the star 51 Pegasi. A normal star, a sun-like star, not a pulsar, not a white dwarf, not a dead anything. A living, hydrogen-burning, perfectly ordinary star about 50 light-years from Earth. The room goes quiet. Then the questions start, and they do not stop for years. The method they used was called radial velocity, also known as the Doppler wobble technique. The idea is elegant. When a planet orbits a star, the planet's gravity tugs on the star just slightly, causing it to wobble back and forth. That wobble shifts the star's light, slightly bluer when the star moves toward us, slightly redder when it moves away. By measuring these tiny shifts with a precise spectrograph, you can infer the presence of an unseen planet, estimate its mass, and calculate its orbital period. Mayer and Queloz had spent years building a spectrograph sensitive enough to detect these wobbles. They installed their instrument, called ELIDY, at the Observatoire de Haute-Provence in southeastern France. Not exactly a glamorous location. A modest observatory on a hilltop in rural Provence, far from the megatelescopes in Hawaii and Chile. But ELIDY was precise enough, and Mayer and Queloz were patient enough, and by the end of 1994 they had data on 51 Pegasi that showed a clear, repeating wobble. A big wobble, bigger than it should have been and faster than anyone thought possible. The planet they found, 51 Pegasi b, had a minimum mass roughly half that of Jupiter. So far, so reasonable. Gas giants were expected. The problem was the orbit. 51 Pegasi b orbited its star in 4.23 days. For comparison, Jupiter takes almost 12 years to orbit the sun Mercury. The closest planet to our sun takes 88 days. This planet was completing a full orbit in the time it takes to binge a Netflix series. It was so close to its star that its surface temperature was estimated at roughly 1,800 degrees Fahrenheit. Every model of planet formation said this was impossible. Gas giants were supposed to form in the cold outer regions of a solar system, where there is enough solid material and low enough temperatures for ice and rock to clump together and attract massive hydrogen and helium envelopes. That is how Jupiter formed. That is how Saturn formed. The inner regions are too hot and too depleted for gas giant formation. A Jupiter-sized planet orbiting closer to its star than Mercury orbits our sun violated everything. Either the models were wrong or the data was wrong. The American planet hunting community, to put it diplomatically, was not immediately supportive. Jeff Marcy and Paul Butler, who were running the most prominent exoplanet search program in the United States from Lick Observatory in California, were blindsided. They had been searching for years and had mountains of data, but they had been looking for planets with long orbital periods like Jupiter's. A 4-day orbit was so far outside their search parameters that they had literally filtered it out. The data for 51 Pegasi was in their observations. They just were not looking for it. The initial skepticism was fierce. Many astronomers suggested that Mayer and Queloz had detected stellar oscillations, not a planet. Stars can pulsate, and those pulsations produce Doppler shifts that can mimic a planetary signal. The wobble pattern needed independent confirmation before anyone would accept it. Marcy and Butler, to their enormous credit, immediately dropped everything and pointed their telescope at 51 Pegasi. Within a week, they confirmed the signal. The planet was real, and Marcy reportedly said, "I was shaking." The confirmation did not end the controversy, though. It just shifted it. If 51 Pegasi b was real, then how did it get there? A gas giant cannot form that close to a star. The temperature is too high for ices to condense, and there is not enough solid material to build a core massive enough to capture a hydrogen envelope. So the planet must have formed further out, where conditions were right, and then moved inward. Migrated. Something pushed or dragged a Jupiter-sized planet from the outer reaches of its solar system to a suicidal orbit right next to its star. The mechanism is called planetary migration. In 1995, it was more of an untested hypothesis than established science. The basic idea is that interactions between a forming planet and the protoplanetary disk of gas and dust it was born and can cause the planet to spiral inward, losing orbital energy and moving closer to the star. It is like a ball rolling down a hill, except the hill is made of gas and gravity, and the ball is a planet the size of Jupiter. If the disk dissipates before the planet reaches the star, the planet stops migrating. If it does not, the planet falls in and dies. 51 Pegasi b, it seemed, had migrated inward and stopped just in time. It was parked in an orbit so close to its star that it was tidally locked, meaning one side permanently faces the star and the other permanently faces away. The day side is a roaring furnace. The night side is cooler but still extremely hot, heated by atmospheric winds that circulate the thermal energy around the planet. The terminator line, the boundary between day and night, is a region of extreme temperature gradients and violent weather. This planet is not a place. It is a condition. The scientific name for this class of planets became hot Jupiters, and the term stuck because it is both accurate and slightly absurd. Hot Jupiters are gas giants, usually between half and twice Jupiter's mass, that orbit their stars in less than about 10 days. They are enormous, blistering hot, and sitting in orbits that should not exist based on any planet formation model that existed before 1995. They are, in the most literal sense, planets that broke the rules. What made 51 Pegasi b even more significant was what it implied about the rest of the galaxy. If one hot Jupiter existed, there were probably more. And if hot Jupiters could form through migration, then planetary systems were not static structures that formed once and stayed put. They were dynamic, chaotic, evolving systems where planets could move, collide, and fall into their stars. Our own solar system, with its neatly separated planets in stable orbits, started to look less like the default template and more like the exception. The floodgates opened fast. Within months of the confirmation of 51 Pegasi b, Marcy and Butler found two more exoplanets, 70 Virginis b, a gas giant in an eccentric orbit, and 47 Ursae Majoris b, a Jupiter-like planet in a more distant, more familiar orbit. Each discovery added another data point. Each data point made the universe weirder. The planet around 70 Virginis had an orbit so elongated that it swung between a relatively cool distance and a scorching close approach, cycling between temperature extremes like a thermal roller coaster. By the late 1990s, the exoplanet count was climbing rapidly, and a pattern was emerging that nobody had predicted. Hot Jupiters were not rare. They were common. Roughly 1 to 2% of Sun-like stars appear to host a hot Jupiter, which sounds small until you multiply it by the hundreds of billions of Sun-like stars in the Milky Way. That is billions of giant planets, each one baking in orbits that our models said should be empty. Billions of impossible worlds, proving that the impossible was actually the norm. The theoretical response was swift. New models of planet formation incorporated migration, disk interactions, gravitational scattering, and tidal circularization. The old picture of solar systems forming neatly and staying put was replaced with a new picture that looked more like a demolition derby. Planets forming in one location, migrating to another, scattering each other into extreme orbits, or ejecting each other entirely. Some planets fall into their stars. Some are flung into interstellar space. And some, the lucky or unlucky ones, end up in stable but bizarre orbits close enough to roast. Michel Mayor and Didier Queloz continued their work, refining their techniques and discovering more exoplanets over the following decades. The significance of their 1995 discovery grew with each passing year as the exoplanet catalog expanded into the thousands. In 2019, 24 years after that announcement in Florence, Mayer and Culo were awarded the Nobel Prize in Physics. The committee cited their discovery of an exoplanet orbiting a solar-type star. It was the first Nobel Prize ever awarded for finding a planet, and the planet they found was a nightmare. There's a beautiful and terrible irony in the story of 51 Pegasi b. Humanity spent centuries dreaming of other worlds. We burned a man alive for saying they existed. We built telescopes, launched observatories, and developed instruments of astonishing precision. And when we finally found a planet around a sun-like star, it was a bloated gas giant with no solid surface, baking at 1,800 degrees Fahrenheit, tidally locked into an orbit so close that it completes a full year in less time than most people spend planning a weekend. The universe gave us what we asked for, just not what we wanted. 51 Pegasi b is still out there. Right now, as you listen to this, it is whipping around its star at roughly 300,000 miles per hour. Its atmosphere is probably a chaotic mess of sodium, potassium, water vapor, and silicate haze. Its winds may exceed several thousand miles per hour. And in about 5 billion years, when 51 Pegasi expands into a red giant, the planet will be engulfed and consumed. But that is a long way off. For now, it spins, it bakes, and it exists as a permanent monument to the moment we discovered that other worlds are nothing like home. Once the dam broke with 51 Pegasi b, the discoveries came fast, and each one arrived with its own special brand of impossibility that forced astronomers to update their models, rewrite their textbooks, or simply stare at the data in confused silence. What follows is not a list. It is a crime scene inventory, because the hot Jupiters that emerged in the late 1990s and early 2000s did not just challenge our understanding of planetary science. They mugged it in an alley and took its wallet. Tau Boötis b was discovered in 1996, just a year after 51 Pegasi b, and it immediately raised the stakes. It orbits the star Tau Boötis, visible to the naked eye in the constellation Boötes, with an orbital period of 3.31 days, even shorter than 51 Pegasi b. This planet is so close to its star that it is tidally locked, meaning one hemisphere permanently faces the stellar furnace while the other faces away into the cold of space. The dayside temperature exceeds 2,500 degrees Fahrenheit. The night side is cooler, but cooler is doing a lot of heavy lifting when we're talking about gas giant atmospheres. What makes Tau Boötis be particularly vicious is the wind. When you have a permanent hot side and a permanent cool side on a gas giant, the atmosphere does not just sit there. It moves violently. Massive atmospheric currents tear across the planet from the day side to the night side, driven by the temperature difference. Models suggest wind speeds of the equatorial regions could exceed 6,000 miles per hour. That is roughly 8 times the speed of sound on Earth. These are not winds in any way a human has ever experienced the word. These are lateral atmospheric detonations. Tau Boötis b also did something unexpected to its star. The planet is so massive and orbits so closely that its gravitational pull has actually synchronized the star's rotation with the planet's orbit. The star rotates once every 3.31 days, matching the planet's orbital period perfectly. The planet is essentially dragging its own star around, a world so powerful it controls the spin of its sun. That is not just a disturbing planet. That is a planet that has taken its star hostage. Then came HD 149026b, discovered in 2005 by a team using the Subaru telescope in Hawaii. This planet is roughly Saturn's mass, which is not unusual. What is unusual is its core. HD 149026b has a core estimated to be around 70 Earth masses of heavy elements, rock and metal packed into its center. For comparison, Saturn's core is estimated at maybe 15 to 20 Earth masses. This planet has a core so disproportionately massive relative to its overall size that no standard formation model can explain it. It is as if someone stuffed a bowling ball inside a basketball. The leading explanation for HD 149026b's bizarre density is that it formed from a merger of two or more smaller planets. In the chaotic environment of a young solar system, collisions between protoplanets are common, but producing something this dense requires a specific and unlikely series of events. Multiple rocky worlds had to collide and merge, then capture a hydrogen and helium envelope, all while migrating inward to its current orbit. It is like winning a very violent, very improbable lottery, and yet the planet exists, which means it happened at least once. HD 149026b is also extremely dark. Later observations by the Spitzer Space Telescope showed that the planet absorbs almost all the starlight that hits it, reflecting very little back. Its dayside temperature reaches approximately 3,700 degrees Fahrenheit, making it one of the hottest planets known at the time of its discovery. It is a scorching dark sphere with an impossibly dense core, orbiting its star every 2.87 days. If you try to describe it to a 1980s astronomer, they would have assumed you were writing science fiction. Bad science fiction. WASP-17b, discovered in 2009 by the Wide-Angle Search for Planets survey, introduced an entirely different kind of impossible. This planet has about half the mass of Jupiter, but is nearly twice Jupiter's diameter. It is, by a significant margin, one of the largest and least dense exoplanets ever found. If you could somehow find a bathtub large enough, WASP-17b would float because its average density is lower than that of styrofoam. It is a giant, puffy, bloated ball of gas with no obvious physical reason for being that inflated. The inflation mystery of hot Jupiters like WASP-17b has been one of the most stubborn puzzles in exoplanet science. Something is pumping extra energy into these planets, puffing them up like cosmic balloons, and for years nobody could figure out what. Theories ranged from tidal heating due to eccentric orbits, to ohmic dissipation where the planet's magnetic field converts wind energy into heat, to simply being closer to a star than any gas giant should reasonably be. As of today, a combination of these mechanisms probably explains the inflation, but the full picture is still incomplete. But WASP-17b had a second trick that was even stranger than its size. It orbits its star backward, retrograde. While the star rotates in one direction, the planet orbits in the opposite direction. This is deeply weird. In our solar system, all major planets orbit the sun in the same direction the sun rotates, because they all form from the same spinning disk of material. A retrograde orbit means something went very, very wrong during this planet's history. Something knocked it off course so dramatically that it ended up going the wrong way around its own star. The most likely explanation is gravitational scattering. At some point in WASP-17b's past, it had a close encounter with another massive planet. The gravitational interaction flung WASP-17b into a highly eccentric, inclined orbit that eventually circularized through tidal interactions with the star, but retained the retrograde orientation. In other words, a planetary game of billiards went so badly that one of the balls ended up rolling backward on the table. And the other ball? Probably ejected from the system entirely, launched into interstellar space to wander forever. We will get to those planets later. Upsilon Andromedae, a star about 44 light-years from Earth, presented yet another flavor of chaos. In 1996, a single planet was discovered orbiting the star. By 1999, two more had been confirmed, making it the first known multi-planet system around a normal star. And the system was a mess. The innermost planet, Upsilon Andromedae b, is a hot Jupiter with a 4.6-day orbit, normal enough by 1999 standards. But the outer two planets had orbits that were wildly misaligned, tilted at extreme angles relative to each other and to the star's equator. In our solar system, all the planetary orbits lie roughly in the same plane, like marbles on a table. In the Upsilon Andromedae system, the orbits are tilted at angles of 30 degrees or more relative to each other. It is as if someone took that table and bent it. The explanation, again, involves violent gravitational interactions. At some point in the system's history, the planets yanked and pulled on each other so aggressively that their orbits were permanently warped. This is not a peaceful solar system. It is a war zone where the combatants happen to be planets. Upsilon Andromedae b, the innermost hot Jupiter, also showed evidence of extreme atmospheric variability. Its dayside and nightside temperatures differ by over 2,500 degrees Fahrenheit, and the hottest point is not directly under the star you might expect, but shifted to one side by atmospheric winds. The wind pattern creates a permanent hot spot that is displaced from the point of maximum stellar heating. Imagine pointing a heat lamp at a spinning ball of gas and having the hottest point be somewhere to the left. The atmosphere is actively fighting the geometry of its own heating. By the early 2000s, the hot Jupiter catalog was growing into something that looked less like a collection of individual curiosities and more like a systematic indictment of everything we thought we knew about planet formation. Each new find added a new violation: extreme densities, impossibilities, retrograde orbits, misaligned systems, temperature extremes that challenge material science. These planets existed in conditions that no model had predicted and no textbook had described. The universe was running an experiment, and we were just now reading the results. And they kept getting weirder. HAT P1b, discovered in 2006, is about half Jupiter's mass, but so bloated that it has roughly the same density as Cork. Ogle TR56b, confirmed in 2003, was one of the first hot Jupiters found using the transit method, orbiting its star in just 29 hours. Trace 4b, found in 2007, was at the time the largest known exoplanet, puffed up to 1.7 times Jupiter's diameter with no satisfying explanation. Each discovery came with an asterisk, a footnote that said, "We do not fully understand why this exists." The phrase hot Jupiter itself became a kind of shorthand for cosmic wrongness. When an astronomer says hot Jupiter, what they really mean is a planet that should not be where it is, should not be the size it is, and probably had to destroy something else to get there. The calm, orderly solar system we grew up learning about in school was turning out to be the exception, not the rule. Most planetary systems in the galaxy are nothing like ours. They're stranger, more violent, and more unpredictable than anything we had prepared for. Perhaps the most unsettling implication of the hot Jupiter discoveries was what they suggested about missing planets. If a gas giant migrates inward from the outer regions of a solar system, it does not travel alone. It plows through the inner system like a wrecking ball, gravitationally destabilizing and ejecting any smaller planets in its path. Rocky planets, Earth-sized planets, potentially habitable planets, all swept aside or consumed by a migrating giant. Every hot Jupiter we find is a crime scene, and the victims are the Earth-like worlds that might have existed before the giant arrived. Think about that for a second. In every system that hosts a hot Jupiter, there were probably once smaller inner planets. Maybe rocky ones, maybe ones with water, maybe ones that, given a few billion years of quiet evolution, might have developed conditions suitable for life. And then a gas giant, formed in the cold outer reaches, spiraled inward and annihilated them. The hot Jupiter, sitting in its scorching orbit, is not just a disturbing planet. It is evidence that other, potentially habitable planets were destroyed to put it there. It is a monument to planetary genocide. By the mid-2000s, the exoplanet field had fully absorbed the shock of hot Jupiters and was hungry for more data. The radial velocity method was powerful but limited. It could detect the presence of a planet, estimate its mass, and determine its orbit. But it could not tell you what the planet looked like, what its atmosphere was made of, or how big it actually was. For that, astronomers needed a different technique. They needed to catch a planet passing in front of its star. They needed the transit method. and the transit method was about to deliver something even the hot Jupiter veterans were not ready for. Finding a planet is one thing. Understanding what it is actually like is something else entirely. The radial velocity method told us a planet existed, gave us its mass and orbit, and then basically shrugged. It could not tell you the planet's size, its density, or what its atmosphere was made of. It was like detecting a criminal by the sound of their footsteps, but never being able to look at them. Useful, but frustrating. Astronomers needed a way to actually see these worlds. And in 1999, they got one. The transit method works on a beautifully simple principle. If a planet's orbit is aligned so that it passes between its star and Earth, the planet will block a tiny fraction of the star's light as it crosses in front. That dip in brightness is measurable, and from that dip, you can calculate the planet's radius. Combine the radius from the transit with the mass from the radial velocity, and you get the planet's density. And density tells you everything. Rock, gas, ice, metal. The transit method turns a distant point of light into a physical object with real properties. The first exoplanet caught in transit was HD 209458b, and the story of its detection is one of those rare moments in science where preparation and luck collide perfectly. The planet had been discovered by radial velocity in November 1999 by a team, including Jeff Marcy. Within weeks, two independent teams, one led by David Charbonneau and the other by Gregory Henry, observed the planet crossing its star. The light dip was about 1.5%, tiny but unmistakable. For the first time, we had seen an exoplanet shadow. HD 209458b quickly earned the nickname Osiris after the Egyptian god of the dead, which turned out to be more appropriate than anyone initially intended. The planet is a hot Jupiter, about 70% the mass of our Jupiter, orbiting its star every 3.5 days at a distance of just 7 million kilometers. For context, Mercury orbits our Sun at about 58 million kilometers. Osiris is more than 8 times closer to its star than Mercury is to ours. The surface temperature clocks in around 1,800 degrees Fahrenheit. It is, by any reasonable definition, a world in torment. But the real breakthrough came in 2001, and it changed exoplanet science forever. A team led by David Charbonneau used the Hubble Space Telescope to observe Osiris during a transit, and for the first time in history, they detected a specific element in the atmosphere of an exoplanet: sodium. They found sodium absorption lines in the starlight filtered through the planet's atmosphere. Think about what that means. We were standing on Earth, looking at a star 150 light years away and tasting the air of an alien world. That is not just science. That is sorcery with better funding. The technique is called transmission spectroscopy, and it works because starlight passing through a planet's atmosphere picks up absorption signatures from whatever chemicals are present. Different molecules absorb different wavelengths of light, leaving distinct fingerprints in the spectrum. By comparing the starlight during a transit with the starlight before and after, you can isolate those fingerprints and identify the atmospheric composition. It is essentially reading a planet's air from 150 light years away. And once astronomers realized they could do this, they could not stop. Follow-up observations of Osiris revealed more than just sodium. In 2003, the Hubble detected hydrogen, oxygen, and carbon in an extended envelope around the planet, material that was not just sitting in the atmosphere, but actively escaping into space. Osiris was losing its atmosphere. The intense radiation from its star was heating the upper atmosphere so violently that gas was boiling off into space in a long, comet-like tail. The planet was evaporating, slowly by human standards, but steadily, relentlessly, and visibly enough that we could watch it happen from another star system. That discovery introduced a concept that would become increasingly important as exoplanet science matured: atmospheric erosion. Planets close to their stars do not just cook, they bleed. The stellar wind and ultraviolet radiation strip material from the upper atmosphere, molecule by molecule, year after year. For smaller planets, This process can be devastating, potentially removing an entire atmosphere over billions of years and leaving behind a bare, scorched rock. Osiris is massive enough to survive, but the implications for smaller worlds were chilling. The transit method's power created a demand for dedicated instruments. Ground-based telescopes could detect transits, but the Earth's atmosphere introduced noise, and you could only observe at night from one location. What astronomers really wanted was a space telescope staring at the same patch of sky continuously, watching thousands of stars simultaneously, waiting for that telltale dip. In 2006, the European Space Agency delivered exactly that with Corot, the convection, rotation, and planetary transit satellite. Corot was not the first space mission to look for exoplanets, but it was the first dedicated exoplanet transit hunter in space. It monitored the brightness of up to 12,000 stars simultaneously for periods of up to 150 days, watching for the tiny dips that betray a crossing planet. It operated for 6 years before a computer failure ended the mission in 2012, and in that time it confirmed 32 exoplanets. That might sound modest compared to what came later, but Corot's discoveries included some of the most significant and disturbing planets in the catalog. Corot also proved a crucial concept. Space-based transit surveys work, and they work at scale. The idea that you could park a telescope in orbit, point it at a field of stars, and robotically detect planets by watching for brightness dips was validated. Corot paved the road for everything that followed, and what followed was the most prolific planet-finding machine in human history. But we will get to Kepler later. First, we need to deal with what Corot and the transit method found when they turned their gaze to rocky worlds. Because here's the thing that nobody fully appreciated until the transit method matured. Detecting an atmosphere is not always good news. Sometimes what you find in that atmosphere tells you something you really did not want to know. Sometimes the spectrum comes back, and the data says this planet's air is made of vaporized metal, or the clouds are made of glass, or the rain is made of iron. The transit method did not just let us find planets. It let us diagnose them, and the diagnosis, more often than not, was terminal. Transmission spectroscopy became a forensic tool. Every transit was a crime scene, and the starlight passing through the atmosphere was the evidence. Astronomers could measure temperature profiles, detect winds, identify clouds, and even determine whether the atmosphere was clear or hazy. The amount of information encoded in a few hours of starlight filtered through an alien sky turned out to be staggering. And with each new observation, the picture of what exoplanets actually look like got darker, more extreme, and more alien than any science fiction writer had ever imagined. By the mid-2000s, the stage was fully set. The radial velocity method had proven that exoplanets existed by the hundreds. The transit method had given us the tools to measure their sizes, calculate their densities, and read their atmospheres. Dedicated space missions were watching the sky with mechanical patience no human could match. And the planet catalog was growing exponentially, with each new entry arriving stranger and more hostile than the last. The question was no longer whether disturbing planets existed. The question was how disturbing they could get. The answer, as the next few chapters will demonstrate, is far more disturbing than anyone was prepared for. Oceans of molten rock, rain made of glass and iron, planets being slowly eaten by their own stars, worlds that survive being swallowed by a dying sun, and atmospheres so toxic, so extreme, and so fundamentally alien that the word weather loses all meaning. The transit method did not just open a window to other worlds. It opened a gallery of horrors, and we had only just walked through the front door. For decades, the dream was simple: find a rocky planet. Gas giants were interesting, sure, but what everyone really wanted was a world with a surface. A world made of rock and metal, like Earth, like Mars, like Venus. A world you could theoretically stand on. The assumption, often unspoken but always present, was that finding a rocky planet would be a step toward finding another Earth. A step toward habitability. A step toward hope. In 2009, Corot found the first confirmed rocky exoplanet. It was not a step toward hope. It was a plunge into a volcano. Corot 7b orbits an orange dwarf star about 489 light-years from Earth. It was detected by the Corot spacecraft in February 2009, and follow-up radial velocity measurements confirmed it was a rocky world about 1.6 times the diameter of Earth and roughly 5 times its mass. A super-Earth. The first one with a confirmed density consistent with a rocky composition. This should have been a celebration, and it was briefly until everybody looked at the orbital period. Corot 7b orbits its star every 20.4 hours. Not days, hours. 20 hours and 24 minutes. That is how long a year lasts on Corot 7b. The planet sits roughly 2.5 million kilometers from its star, about 60 times closer than Earth is to the Sun. At that distance, the dayside temperature reaches approximately 4,200 degrees Fahrenheit. For reference, lava on Earth erupts at around 2,200 degrees Fahrenheit. Corot 7b's surface is nearly twice as hot as flowing lava. At those temperatures, rock does not just melt, it vaporizes. The surface of the dayside is a churning ocean of liquid magma under an atmosphere of rock vapor. Let that image settle in your mind. An ocean of lava, not a lake, not a flow, not a river. An ocean, stretching from horizon to horizon on the permanent dayside of this tidally locked world, glowing orange and white under a sky filled with vaporized silicates. The rock literally boils off the surface, rises into the atmosphere as gas, and gets carried by atmospheric circulation toward the night side. This is not geology as we understand it. This is geology having a nervous breakdown. Corot 7b is tidally locked, like most planets this close to their stars. One side always faces the stellar furnace. The other side faces the cold void of space. The temperature difference between the two hemispheres is extreme, potentially thousands of degrees. The night side might actually have a solid rock surface, cooled enough to crystallize, while the day side is a permanent magma sea. The terminator, the boundary between day and night, would be a zone of constant geological violence, solidifying lava meeting liquid rock with a vaporized rock atmosphere swirling overhead. Models of Corot 7b's atmosphere suggest it is composed primarily of sodium, potassium, silicon monoxide, and other vaporized rock constituents. Not oxygen and nitrogen like Earth. Not carbon dioxide like Venus. Literally vaporized minerals. The sky on the day side is made of the same stuff as the ground, just in gas form. If weather exists on Corot 7b, and models suggest it does, then the forecast would be something like partly cloudy with a chance of condensing rock droplets and magma showers. Every single day. Forever. 2 years later, in January 2011, NASA's Kepler Space Telescope confirmed its first rocky planet, Kepler 10b. And it was, if anything, even worse. Kepler 10b orbits its star every 20 hours, sits at a similar scorching distance, and has a dayside temperature of roughly 2,500 degrees Fahrenheit. Its density, however, is remarkable. Kepler 10b is the densest small exoplanet known, with a density about 8.8 grams per cubic centimeter. Earth's density is 5.5. Iron's density is 7.9. This planet is denser than iron. Its core is almost certainly a massive ball of molten metal. Kepler 10b is roughly 1.47 times Earth's diameter, but its mass is about 4.6 times Earth's. The surface gravity is roughly twice what you would feel on Earth. If you could somehow stand on the night side without being incinerated by residual heat, you would weigh twice what you weigh now, struggling to breathe an atmosphere of metal vapor, looking up at a sky that glows faintly from the reflected light of a molten hemisphere just over the horizon. It is a world where the ground is liquid, the air is rock, and gravity is trying to press you into the floor. These early lava worlds were shocking, but they were just the appetizers. The main course arrived in 2017 with the discovery of K K2141b, a planet that took the concept of a lava world and turned it into something that would make Dante Alighieri say, okay, that is a bit much. K2141b is a super-Earth about 1.5 times the diameter of our planet, orbiting a K-type orange dwarf star every 6.7 hours. 6.7 hours. This planet completes a full orbit in less time than a decent night's sleep. The dayside temperature of K2141b exceeds 5,400 degrees Fahrenheit. At that temperature, not only does rock melt and vaporize, but some rock components actually dissociate, breaking down into their elemental atoms. The surface is a magma ocean estimated to be at least 60 miles deep. The atmosphere above it is composed of silicon dioxide, sodium, and other vaporized rock minerals. Winds carry this rock vapor from the day side to the night side at supersonic speeds. And then something extraordinary happens. On the night side of K2141b, where temperatures are lower, the rock vapor in the atmosphere cools and condenses. It forms droplets. It rains, except it does not rain water. It rains rocks. Pebbles of solidified minerals fall from the sky onto the nightside surface. Those pebbles accumulate, forming a rocky surface layer that slowly flows back toward the day side, driven by the pressure differential and the planet's geology. On the day side, the rock melts again, vaporizes again, rises into the atmosphere again, and the cycle repeats. It is a complete weather cycle made entirely of stone. Scientists at McGill University and York University published a detailed model of this cycle in 2020, and the parallels to Earth's water cycle are uncanny and horrifying. On Earth, water evaporates from the ocean, rises into the atmosphere, forms clouds, gets carried by wind, condenses as rain, and flows back to the ocean through rivers. On K2141b, rock evaporates from the magma ocean, rises into the atmosphere, forms mineral clouds, gets carried by supersonic winds, condenses as pebble rain, and flows back to the magma ocean through magma rivers. Same process, different material, incomprehensibly worse. The magma rivers on K2141b deserve their own moment of horrified appreciation. These are not like lava flows on Earth, where molten rock oozes slowly down a volcano's slope. These are continent-spanning rivers of liquid rock, flowing across the night-side surface toward the day side under the influence of pressure differentials and the planet's rotation. They glow, they churn, they carry dissolved minerals and heat from one hemisphere to the other in a geological conveyor belt that operates at temperatures hot enough to melt steel. Rivers of lava, hundreds of miles wide, flowing endlessly toward a horizon that burns. K2141b also highlights a concept that applies to many of these extreme worlds. The lava planet is not a static hellscape. It is a dynamic system. It has weather. It has geology. It has atmospheric circulation and precipitation and surface flow. It is doing all the things a planet is supposed to do, just with rock instead of water, at temperatures that would vaporize a spacecraft before it got within 100 miles of the surface. The machinery of a planet works the same way everywhere. The universe just plugs in different materials depending on how close to a star you are. The question that haunted researchers after these discoveries was, how many lava worlds are out there? The answer appears to be a lot. Any rocky planet orbiting close enough to its star will have its day side melted. And close orbits are common because they're the easiest to detect. Our catalog is biased toward finding these things. But even accounting for that bias, models suggest that rocky planets and scorching orbits are extremely common across the galaxy. There could be billions of them in the Milky Way alone, billions of magma oceans, billions of stone skies, billions of worlds where the concept of solid ground is a part-time condition. What makes lava planets genuinely disturbing beyond the obvious surface conditions is what they tell us about the fragility of habitability. Move Earth just a few percent closer to the sun, and our oceans start to boil. Move it closer still, and the surface melts. The difference between a habitable rocky world and a screaming lava hellscape is not some vast cosmic margin. It is a relatively small orbital adjustment. The line between paradise and inferno is thin, and the universe has clearly landed on the inferno side far more often than the other. Lava worlds also raise uncomfortable questions about Earth's own past. 4.5 billion years ago, shortly after the giant impact that formed the Moon, Earth's surface was a global magma ocean. Our planet was, for a brief period in geological time, a lava world. The entire surface was molten. The atmosphere was vaporized rock. It rained minerals. Sound familiar? Earth went through its own lava planet phase and survived. The difference is that Earth was far enough from the Sun for the surface to eventually cool. Corot 7b, Kepler 10b, and K 2141b are not that lucky. Their inferno is permanent. So there it is. The first rocky planets we found outside our solar system were not gentle, blue, water-covered worlds with meadows and moderate climates. They were screaming hellscapes of liquid rock and mineral rain. Every medieval painting of hell, every fire and brimstone sermon, every volcanic nightmare a human has ever had, all of them fall short of what actually exists on these worlds. And they exist in numbers that dwarf anything we are equipped to comprehend. The rocky planet dream was not dead, but it was standing ankle-deep in magma, and it was not smiling. Everything dies. Stasti, galaxisti. The universe itself will eventually wind down into a cold, empty nothing. But there's something uniquely unsettling about watching a planet die. Not in the abstract, not in the theoretical, but in the literal, observable, measurable sense. Some planets out there are being destroyed right now, in real time, and we can see it happening. Their stars are eating them alive, and the process is exactly as violent as it sounds. WASP-12b was discovered in 2008 by the Super-WASP survey, and from the moment its parameters were published, it was clear this planet was living on borrowed time. It is a hot Jupiter about 1.4 times the mass of our Jupiter, orbiting a sun-like star roughly 1,400 light-years from Earth. Its orbital period is 1.09 days, just over 26 hours. It sits roughly 3.4 million kilometers from its star, which is so close that the boundary between orbiting and falling in becomes a matter of philosophical debate. At that distance, the star's gravitational tidal forces are immense. They stretch WASP-12b into an egg shape, a process called Roche lobe overflow. The planet is literally being pulled apart at the seams. Material from its outer atmosphere is being siphoned off, streaming away from the planet in a spiraling river of superheated gas that falls toward the star. Hubble observations have confirmed a diffuse cloud of gas surrounding the planet, material that has been ripped away and now orbits the star independently. The planet is bleeding into space. The rate of mass loss is staggering. Estimates suggest WASP-12b is losing roughly 189 quadrillion tons of material per year. That is 189 followed by 15 zeros per year. At that rate, the planet will be completely consumed in roughly 10 million years. That sounds like a long time by human standards, but in cosmic terms, it is nothing. The universe is 13.8 billion years old. 10 million years is a rounding error. WASP-12b is not dying slowly. It is dying fast. We just happen to be watching at the right moment. There is something else about WASP-12b that caught astronomers off guard. The planet is dark, extremely dark. In 2017, observations from the Hubble Space Telescope showed that WASP-12b reflects almost no visible light. Its albedo, the fraction of light it reflects, is less than 0.064. For comparison, Earth's average albedo is about 0.30. The Moon's is 0.12. WASP-12b is darker than fresh asphalt, a dying planet wrapped in darkness, being devoured by its star. If a poet wrote that, you would say it was too on the nose. But the universe does not care about subtlety. The reason for the darkness is probably the extreme temperature. WASP-12b's dayside reaches about 4,600 degrees Fahrenheit, hot enough to break apart hydrogen molecules and prevent the formation of reflective clouds. Most hot Jupiters have clouds of some kind that reflect at least some starlight. WASP-12b is too hot even for that. Its atmosphere absorbs almost everything that hits it, converting starlight into heat with terrifying efficiency. It is an oven wrapped in a void, spiraling toward annihilation, and it does not even have the courtesy to shine while it dies. Let us return briefly to Osiris, HD 209458b, because the atmospheric escape story gets worse with time. After the initial detection of escaping hydrogen in 2003, subsequent observations revealed that the atmospheric loss was more dramatic than initially thought. The escaping gas extends in a vast cloud around the planet, creating a sort of cometary envelope that trails behind it in its orbit. Carbon and oxygen were also detected in the escaping material, meaning the planet is not just losing light hydrogen. It is losing heavier elements too. The atmosphere is being comprehensively dismantled. The Osiris data raised a profound question. If a planet as massive as this hot Jupiter, roughly 70% of Jupiter's mass, is losing its atmosphere at a measurable rate, what happens to smaller planets in similar orbits? A super-Earth or a mini-Neptune parked that close to a star would have far less gravitational grip on its atmosphere. The stellar radiation would strip it bare in a fraction of time. And that, scientists realized, is probably exactly what has happened to many planets. We see a gap in the exoplanet size distribution, a scarcity of planets between 1.5 and 2 Earth radii, that likely represents the graveyard of worlds that lost their atmospheres entirely. This gap is called the Fulton Gap or the Radius Valley, and it is one of the most significant patterns in the Kepler data. Below the gap, you find rocky planets that either never had thick atmospheres or lost them long ago. Above the gap, you find gaseous planets that manage to hold onto their hydrogen and helium envelopes. In between, there's almost nothing. The planets that should be there are missing. They were stripped, eroded, peeled down to their rocky cores by billions of years of stellar radiation. An entire class of worlds silently destroyed. WASP-121b, discovered in 2015, added a new wrinkle to the story of planetary death. This hot Jupiter orbits its star every 1.27 days and has a dayside temperature of about 4,600 degrees Fahrenheit. But the truly bizarre aspect of WASP-121b is its temperature inversion. In most planetary atmospheres, including Earth's lower atmosphere, temperature decreases with altitude. On WASP-121b, the upper atmosphere is actually hotter than the lower atmosphere. The temperature goes up as you go higher. The atmosphere is heated from the top down, not the bottom up. The cause of the temperature inversion appears to be vanadium oxide and titanium oxide in the upper atmosphere. These metal oxides absorb incoming starlight at high altitude, heating the upper layers while the lower layers remain relatively cooler. It is essentially a natural sunscreen effect, except the sunscreen is made of vaporized metal, and the result is an atmosphere that defies intuitive thermal structure. On Earth, hot air rises. On WASP-121b, the hottest air is already at the top, creating a stable stratosphere of superheated metal vapor that just sits there, broiling. WASP-121b is also losing its atmosphere, but the process here is particularly dramatic. The planet is close to its Roche limit, the distance at which tidal forces will tear it apart entirely. Material is streaming off the planet in visible quantities, and the planet's shape is measurably distorted by tidal forces. Its atmosphere extends so far from the planet's center that the outermost layers are barely gravitationally bound. In 2019, Hubble detected iron and magnesium in the escaping atmospheric material. Not just gas, metals. The planet is sweating iron into space. The JWST observations of WASP-121b, published starting in 2023, were even more revealing. The telescope mapped the planet's atmosphere in 3 dimensions, tracking how temperature and chemistry change not just with altitude, but across longitude, from day side to night side. The results showed a dramatic chemical gradient. On the day side, molecules are torn apart by heat. On the night side, they recombine. The atmosphere is in a constant cycle of destruction and reformation, a chemical conveyor belt driven by extreme temperature contrasts and supersonic winds. What these dying planets share is not just extreme heat or close orbits. They share a timeline. Every one of them is on a clock. WASP-12b has maybe 10 million years. WASP-121b is being stripped and distorted. OSIRIS is bleeding into space. In each case, the endpoint is the same. The planet will be destroyed, either consumed by its star, stripped to a bare core, or tidally ripped apart. These are not permanent features of the universe. They are temporary objects caught in the brief window between formation and annihilation. We are watching their final acts. There is a philosophical dimension to this that is worth sitting with for a moment. We tend to think of planets as permanent. Earth has been here for 4.5 billion years. It will be here for billions more. Planets, in our experience, are the most stable, most enduring things in the solar system. But WASP-12b shatters that assumption. Planets can die. Planets do die. And they die not in some distant, abstract future, but on timescales that are cosmically instantaneous. The universe creates worlds and then destroys them with the same indifferent efficiency. And perhaps the most disturbing thought of all, we only see the ones that are dying now. For every WASP-12b we observe mid-destruction, there are countless planets that have already been consumed. Stars that appear alone and planetless today may have once hosted entire systems that spiraled inward and were devoured, leaving no trace. The star absorbed them. The evidence is gone. We will never know how many worlds died before we had the technology to watch. The graveyard is full, and we arrived too late to count the bodies. WASP-12b is still out there right now, still orbiting, still losing mass, still being stretched and heated and slowly torn apart by a star that does not know or care that something is dying in its gravitational embrace. In 10 million years, give or take, it will be gone entirely. Just another quantity of gas absorbed into a stellar atmosphere, indistinguishable from the star itself. No monument, no crater, no evidence it was ever there. A planet unmade, as if it never existed at all. Here is a photograph for you. Well, not exactly a photograph, but the closest thing we have. HD 189733b, as imaged in reflected light, is a deep, stunning cobalt blue. It is one of the most visually striking exoplanet images ever captured. If you saw it on a poster without context, you might think it was a water world, an alien ocean planet, something beautiful and possibly even welcoming. You would be catastrophically wrong. HD 189733b is not blue because of water. It is blue because of glass. And that glass is falling sideways at 5,400 miles per hour. HD 189733b was discovered in 2005, orbiting a star about 64 light-years from Earth. It is a hot Jupiter, slightly more massive and slightly larger than our Jupiter, completing an orbit every 2.2 days. Its dayside temperature reaches approximately 1,700 degrees Fahrenheit. All of that is fairly standard for a hot Jupiter by 2005 standards. What is not standard is the atmosphere. In 2007 and 2008, observations by the Hubble and Spitzer space telescopes began revealing the atmospheric composition, and the results were unlike anything previously documented. The blue color comes from silicate particles suspended in the atmosphere. Silicates are the minerals that make up most rocks on Earth. Quartz, feldspar, mica. On HD 189733b, these minerals exist as tiny particles in the atmosphere, and they scatter blue light very efficiently, the same way Earth's atmosphere scatters blue light to give us blue skies. But on Earth, the particles are nitrogen and oxygen molecules. On HD 189733b, the particles are molten glass. The sky is blue for essentially the same reason. The material making it blue is just infinitely more lethal. Now, those silicate particles do not just float around harmlessly. The temperature difference between the day side and night side drives atmospheric winds of extraordinary violence. Measurements suggest wind speeds on HD 189733b reach approximately 5,400 miles per hour. That is roughly 7 times the speed of sound on Earth. At those speeds, the molten glass particles in the atmosphere are not drifting. They are being fired horizontally like bullets from shotgun. If you were somehow standing on this planet, you would be sandblasted by sideways glass rain traveling at 7 times the speed of sound. You would not last a second. In 2013, astronomers using the Hubble Space Telescope actually observed HD 189733b change color during a transit, providing further evidence of the extreme atmospheric dynamics. The planet's atmosphere is not uniform. It shifts and churns, with hotter and cooler regions creating variations in the silicate cloud cover. The blue color deepens or lightens depending on what part of the atmosphere faces the observer. Even by exoplanet standards, this world's weather is volatile and violent in ways that defy comfortable description. HD 189733b also holds the distinction of being the first exoplanet for which a weather map was produced. Spitzer Space Telescope data allowed scientists to map the temperature distribution across the planet's surface, revealing that the hottest point is not directly beneath the star, but offset to the east by atmospheric winds. The temperature peaks at over 1,700 degrees on the day side and drops to about 1,200 degrees on the night side. That night side temperature is still hot enough to melt aluminum. There is no safe side of this planet. There is only the slightly less immediately fatal side. If HD 189733b was the planet that introduced us to weaponized weather, WASP-76b was the planet that perfected it. Discovered in 2013 and characterized in spectacular detail by 2020, WASP-76b is a hot Jupiter orbiting a star about 640 light-years from Earth. Its orbital period is 1.81 days. Its dayside temperature exceeds 4,300 degrees Fahrenheit. And on its night side, it rains iron. Not metaphorically, not poetically, literally, measurably iron. The mechanism is both elegant and horrifying. On the permanent day side of WASP-76b, the temperature is so extreme that iron, one of the most heat-resistant common metals, vaporizes. Iron atoms float freely in the atmosphere as gas, mixed with other vaporized metals and minerals. Atmospheric circulation then carries this iron-laden gas from the day side toward the night side. As the gas crosses the terminator into the cooler night side, the temperature drops enough for the iron vapor to condense into liquid droplets. Iron rain, droplets of molten metal falling from the sky. The evidence came from the espresso spectrograph on the European Southern Observatory's Very Large Telescope in Chile. A team led by David Ehrenreich observed WASP-76b during transit and detected a strong iron absorption signal on the evening terminator, the boundary where the day-side atmosphere transitions to the night side. But on the morning terminator, the iron signal was absent. The iron was present in the gas on one side and gone on the other. It had condensed and fallen out of the atmosphere. Rained down. The data was so clean and so striking that even the researchers were startled. Try to picture that night side for a moment. You are standing in permanent darkness because this side of the planet never faces the star. The sky above you is thick with metal vapor carried over from the blazing hemisphere on the other side. And then it starts to rain. Not water, not ice, iron. Droplets of molten iron, glowing faintly orange from residual heat, falling through a dark sky onto a surface that nobody has ever seen or characterized. A black rain of liquid metal in permanent night. That is not weather. That is a punishment. Subsequent analysis suggested that WASP-76b's atmosphere contains more than just iron. Calcium, sodium, lithium, potassium, manganese, and other metals and minerals were detected. The atmosphere is essentially a vaporized mineral soup, a cocktail of elements that on Earth exist exclusively as solids. On WASP-76b, there are gases on one side and precipitation on the other. The periodic table is not just a chart on this planet. It is the weather forecast. HAT P7b, discovered in 2008 and studied extensively in the years that followed, brought yet another variation to the nightmare weather theme. This planet is a hot Jupiter about 1,040 light-years away, orbiting its star every 2.2 days. Its dayside temperature reaches roughly 4,700 degrees Fahrenheit. What makes HAT P7b special is its clouds. They are made of corundum, aluminum oxide, the mineral that, in crystal form, is known as ruby and sapphire. This planet has clouds of rubies and sapphires. If that sounds beautiful, it is right up until you learn what happens with those clouds. In 2016, a team using data from the Kepler spacecraft discovered that the brightest point on HAT P7b's surface shifts position over time. The bright spot, which represents the area of maximum reflected light and presumably the thickest cloud cover, moves unpredictably from one side of the day side to the other. This is weather variability on a massive scale. The cloud patterns change, the winds shift, and the entire weather system of the planet reorganizes itself repeatedly. Nothing is stable. Nothing is predictable. This was the first observational evidence of large-scale weather variation on an exoplanet. On Earth, weather changes constantly, and we take it for granted. But proving that weather changes on a planet hundreds of light-years away, using only the tiny fluctuations in reflected starlight, was a genuine breakthrough. It also meant that the nightmare weather on these planets is not static. It is not a permanent, fixed pattern. It changes. It shifts. It is actively, dynamically, unpredictably hostile. Even the horror is variable. There is a dark irony running through all three of these planets. They are, in their own terrifying way, beautiful. HD 189733b is a gorgeous blue. WASP-76b's iron rain probably creates shimmering curtains of glowing metal in its dark sky. HAT P7b literally has clouds made of gemstones. If you could somehow view these worlds from a safe distance, protected from the heat and the wind and the radiation, they might be the most visually stunning things in the galaxy. Beauty and lethality, wrapped together so tightly you cannot separate them. Earth's most violent weather event, by comparison, is almost embarrassingly mild. The strongest recorded wind gust on Earth was 253 miles per hour during Tropical Cyclone Olivia in 1996. HD 189733b's winds are more than 20 times that speed. The heaviest rainfall rate ever recorded on Earth was about 12 inches in 1 minute in Unionville, Maryland in 1956. WASP-76b rains molten iron. The most destructive hailstone on Earth weighed about 2 pounds. HAT P7b drops sapphires. There is no comparison. These planets do not have weather. They have weapons. And this is what the transit method brought us. Not just the detection of planets, but the diagnosis of their atmospheres, the measurement of their winds, the identification of their cloud compositions, and the mapping of their temperature distributions. Each observation peels back another layer and reveals another impossibility. Glass rain, iron rain, gemstone clouds, supersonic storms. The transit method turned exoplanet science from a detection game into a forensic analysis of alien environments. And the forensic report, almost without exception, reads, hostile beyond imagination. These weather systems exist right now as you hear these words. Somewhere out there, 64 light-years away, glass is falling sideways through a blue atmosphere at Mach 7. Somewhere else, 640 light-years away, iron is condensing out of a dark sky. And on yet another world, Clouds of ruby and sapphire are forming, breaking apart, and reforming in patterns that no model can fully predict. The universe runs these experiments continuously, on billions of planets, in conditions that make Earth's most violent weather look like a pleasant afternoon. Our planet storms are not normal. They are exceptionally, almost miraculously, gentle. We have talked about planets that are being destroyed, planets being stripped, devoured, and slowly unmade by the forces around them. But there's a category of exoplanet that is, in some ways, even more disturbing. Not planets that are dying, planets that should already be dead, planets that survived events so catastrophic, so fundamentally unsurvivable, that their continued existence challenges everything we know about how stellar systems work. These are the impossible survivors, and the most extreme of them orbited inside its own star. Kepler 70b was announced in 2011, discovered by a team led by Stefan Charpentier using data from the Kepler Space Telescope. The host star, Kepler 70, also known as KIC 5807616, is a subdwarf B star. That classification is important. Subdwarf B stars are the stripped cores of former red giant stars. They have shed their outer hydrogen envelopes and are now small, hot, compact objects. Kepler 70 already went through its red giant phase. It already expanded. It already swallowed anything that was too close. And yet, somehow, there are planets orbiting inside where the red giant's envelope used to be. Kepler 70b orbits its star every 5.76 hours, 5 hours and 45 minutes. The orbital distance is roughly 0.006 astronomical units from the star. For comparison, Mercury, our closest planet to the Sun, orbits at 0.39 AU. Kepler 70b is roughly 65 times closer to its star than Mercury is to the Sun. At that distance, during the red giant phase, the star's outer envelope would have extended well beyond the planet's orbit. The planet would have been submerged inside the star, swimming in stellar plasma, and it survived. Let that concept settle. A planet orbited inside a star. Inside it, not near it, not close to it, but actually embedded within the outer layers of a bloated red giant. The conditions inside a red giant's envelope are not subtle. Temperatures of tens of thousands of degrees, crushing plasma density, intense radiation. Nothing recognizable as a planet should survive that environment. And yet Kepler 70b apparently did. Or at least, something that used to be part of a larger planet survived. What emerged from the star was almost certainly not what went in. Kepler 70c is the companion planet, orbiting every 8.23 hours at a similarly absurd distance. Together, the two planets orbit so close to each other that their mutual distance can be as small as 240,000 kilometers, closer than the Moon is to Earth. If you stood on Kepler 70b and looked up, Kepler 70c would appear enormous in the sky, a looming world close enough to see surface detail, if either world had any surface detail left to see. Two scorched remnants, practically touching, racing around the ember of their former sun. The surface temperature of Kepler 70b is estimated at approximately 12,000 degrees Fahrenheit. 12,000. For reference, the surface of our sun is about 10,000 degrees Fahrenheit. Kepler 70b is hotter than the surface of the sun. It is a planet that is, by temperature, more star-like than planet-like. Whatever material comprises its surface, it is glowing white-hot, radiating energy like a small stellar body. Calling it a planet, at this point, is almost a semantic generosity. It is a superheated remnant that happens to orbit something. The leading theory about what Kepler 70b and Kepler 70c actually are is both elegant and grim. They are probably the exposed cores of former gas giant planets. Before the star expanded, these worlds may have been Jupiter or Saturn-sized gas giants in relatively normal orbits. As the star entered its red giant phase and expanded, it engulfed the planets. The outer layers of hydrogen and helium were stripped away by friction and heating, like sandblasting a balloon down to its inner knot. What survived was the dense, metallic, rocky core, the skeleton of a planet. This stripping process also explains their current orbits. As the planets plowed through the dense stellar envelope, they experienced enormous drag. That drag bled away their orbital energy, causing them to spiral inward, closer and closer to the stellar core. When the red giant phase ended and the star shed its outer layers to become a subdwarf B star, the planets were left behind in the tight orbits where drag had deposited them. They did not choose to orbit this close. They were dragged there by the dying convulsions of their own sun. Survivors, yes, but survivors in a prison. There is ongoing scientific debate about whether the Kepler 70 detections are genuine planets or an artifact of the data analysis. Some researchers have argued that the signals could be caused by reflected light from stellar pulsations rather than actual orbiting bodies. The original detection method, which used pulsation timing rather than traditional transits, is less established and more susceptible to false positives. As of the mid-2020s, the existence of Kepler 70b and 70c is considered plausible but not as firmly confirmed as many other exoplanets. The universe may be hiding its survivors in ambiguity. But whether Kepler 70b specifically holds up or not, the concept it represents is real and well-supported. Planetas do Survive Stellar engulfante. We have strong theoretical models showing how a dense enough core can resist dissolution inside a red giant's envelope, especially if the engulfment phase is relatively brief, a few million years. And we have other examples. Several planets have been found in tight orbits around post-red giant stars, compact objects that bear the scars of having been through the fire. These are confirmed worlds that rode through the belly of a dying star and came out the other side. Consider the case of V391 Pegasi b. This planet, reported in 2007, orbits a subdwarf B star similar to Kepler 70. The planet is a gas giant, about 3.2 times Jupiter's mass, orbiting at a distance that would have placed it inside the star's red giant envelope. It is further evidence that at least some planets can survive the most extreme phase of their star's life. Not unscathed, not unchanged, but intact enough to keep orbiting. Battered survivors circling the ruins of their former sun, like someone standing in the wreckage of their house and refusing to leave. Then there are planets that survived a different kind of catastrophe entirely. PSRB 1620-26b, sometimes called Methuselah, orbits a binary system consisting of a pulsar and a white dwarf in the globular cluster M4. This planet is estimated to be about 12.7 billion years old, nearly 3 times the age of Earth, and almost as old as the universe itself. It has survived the death of not one, but 2 companion stars, plus billions of years in the dense, gravitationally chaotic environment of a globular cluster where close stellar encounters are common. Methuselah's existence implies a level of resilience that borders on absurd. Globular clusters are gravitationally intense environments where stars pass close to each other regularly. Each close encounter risks disrupting planetary orbits through gravitational perturbation. Over 12.7 billion years, the number of potential disruptions is enormous. And yet the planet is still there, still orbiting, still intact. It watched the universe go from a hot, dense soup of hydrogen and helium to the galaxy-spanning web of structure we see today. It was there before Earth's sun even ignited. Gravitational slingshots provide another mechanism of survival through violence. In chaotic multi-planet systems, gravitational interactions can fling planets into wildly different orbits. Some are ejected entirely, becoming rogue planets. But some are flung into orbits that are extreme but stable, high eccentricity paths that take them from close to their star out to enormous distances and back again. These planets were not born in those orbits. They were thrown there by encounters with other planets. Survivors of a gravitational bar fight, stumbling home on a path they did not choose. HD 80606b is a perfect example. This gas giant, discovered in 2001, has one of the most eccentric orbits of any known exoplanet. Its distance from its star varies by a factor of 30 during each orbit. At its farthest point, it is about as far from its star as Earth is from the Sun. At its closest, it is 20 times closer than Mercury is to ours. The temperature swing during each orbit is extreme, from a few hundred degrees at Apastron to over 2,000 degrees at Periastron, all in the span of its 111-day orbital period. A planet on a permanent roller coaster between freezing and broiling. Spitzer Space Telescope observations actually caught HD 80606b during a close approach to its star. In just 6 hours, the planet's dayside temperature spiked from about 980 degrees Fahrenheit to over 2,240 degrees Fahrenheit. The atmosphere responded with violent storm formation visible in the thermal data. The planet essentially goes through a weather apocalypse every time it swings close to its star, then cools down as it retreats, only to be blasted again on the next approach. It is not weather. It is periodic thermal assault. The common thread across all these survivors is resilience in the face of cosmic violence. Engulfed by dying stars, irradiated by pulsars, flung into extreme orbits by gravitational chaos, battered for billions of years in hostile cluster environments. These planets absorbed levels of punishment that should have ended them, and they endured, not because they're special, not because the universe was merciful, but because the physics happened to work out in their favor by the thinnest of margins in the most extreme of circumstances. And that, perhaps, is the most unsettling takeaway. The universe does not guarantee destruction any more than it guarantees creation. Things survive that should not survive. Things persist that should have been obliterated. The rules are not clean and absolute. They are probabilistic, messy, and occasionally merciful in ways that feel almost accidental. Kepler 70b might be a planet that rode through the interior of a star and emerged as a glowing metallic remnant. If that can happen, then our assumptions about what is and is not possible in the cosmos need serious revision. The universe does not always finish the job, and the things that survive are not always better for it. On March 7th, 2009, a Delta II rocket lifted off from Cape Canaveral carrying a 1-ton telescope named after Johannes Kepler, the 17th century astronomer who figured out that planets move in ellipses, not circles. The telescope's mission was simple in concept and staggering in ambition. Stare at a single patch of sky containing roughly 150,000 stars and watch for the tiny, periodic brightness dips that betray a planet crossing in front of its star. Do not blink. Do not look away. Just watch. For 4 years straight. The patch of sky Kepler chose was in the constellations Cygnus and Lyra, a region rich with sun-like stars at manageable distances. The telescope's photometer was exquisitely sensitive, capable of detecting brightness changes as small as 20 parts per million. That is like watching a stadium floodlight from a mile away and noticing when a gnat flies across it. Every 30 minutes, Kepler recorded the brightness of all 150,000 target stars simultaneously, building up light curves that stretched over months and years, hunting for the rhythmic dips that signal an orbiting planet. The data started arriving in torrents. By 2010, Kepler had already identified hundreds of planet candidates. By 2013, the number was in the thousands. And the candidates were not just hot Jupiters, the easy catches. Kepler was finding small planets, rocky planets, planets in the habitable zone, planets in multi-planet systems, planets orbiting binary stars, planets in configurations that nobody had predicted and many had explicitly declared impossible. The universe, it turned out, had been building solar systems with considerably more imagination than we had given it credit for. In May 2013, a reaction wheel failed on the spacecraft. Reaction wheels are spinning gyroscopes that keep the telescope pointed precisely at its target. Kepler needed 3 working wheels to maintain its aim, and now it had only two. The primary mission was effectively over. NASA engineers, in an impressive display of stubbornness, figured out how to use solar radiation pressure as a third stabilization axis, creating a modified mission called K2 that continued discovering planets until the spacecraft ran out of fuel entirely in October 2018. Even half-broken, Kepler refused to stop finding nightmares. By the end of its operational life, Kepler had confirmed 2,662 exoplanets. It had identified over 4,000 additional candidates awaiting confirmation. It had demonstrated that, statistically, there are more planets than stars in our galaxy. It had found planets ranging from smaller than Mercury to larger than Jupiter, in orbits ranging from hours to years, around stars ranging from tiny red dwarfs to blue giants. The Kepler data set is, without exaggeration, the most comprehensive survey of alien worlds ever conducted. And buried in that data are some of the most disturbing individual planets ever discovered. Let us start with Kepler 78b, because Kepler 78b should not exist, and it knows it. Discovered in 2013, this planet is roughly the same size and mass as Earth. A true Earth analog in terms of physical properties, except it orbits its star every 8.5 hours. 8.5 hours. A year on Kepler 78b lasts about as long as a workday. The planet orbits so close to its star that the surface temperature exceeds 3,600 degrees Fahrenheit. The entire surface is molten. Whatever Kepler 78b once was, it is now a glowing ball of lava roughly the size of our world. The problem with Kepler 78b is not just that it exists in a hellish orbit. The problem is that it cannot have formed there, and it cannot have migrated there. It is too close. When the star was young and had a protoplanetary disk, the inner edge of that disk would have been further out than Kepler 78b's current orbit. There is no material where the planet now sits for it to have formed from. And migration models struggle to park a planet that close without it falling into the star entirely. By every known formation mechanism, Kepler 78b should not be where it is. Yet there it sits, glowing and defiant. Kepler 78b is also doomed. Tidal interactions with its star are causing its orbit to decay. The planet is spiraling inward, slowly but measurably, and in a few billion years it will cross the Roche limit and be torn apart by tidal forces or simply plunge into the star. It is a planet with a death sentence, living out its remaining time in an orbit that physics says it should never have occupied in the first place. Born impossible, dying inevitable. There's a poetry to that, though it is not particularly cheerful poetry. Kepler 36b and Kepler 36c offer a completely different flavor of impossible. These two planets orbit the same star, Kepler 36, and they do so in orbits that are disturbingly, almost offensively close to each other. Kepler 36b is a rocky super-Earth about 1.5 times Earth's diameter. Kepler 36c is a mini-Neptune about 3.7 times Earth's diameter. Their orbital periods are 13.8 days and 16.2 days, respectively. The ratio of those periods is almost exactly 7:6. They're locked in what is called a near resonance, and it brings them terrifyingly close together on a regular basis. Every 97 days, the two planets reach their closest approach, a conjunction where they pass within about 1.9 million kilometers of each other. That sounds like a lot until you realize that the Moon is about 384,000 kilometers from Earth. These two planets pass within roughly 5 times the Earth-Moon distance, and Kepler 36c, the larger planet, is nearly 4 times the diameter of Earth. From the surface of Kepler 36b, during closest approach, Kepler 36c would appear in the sky roughly 2.5 times the diameter of our full Moon. A massive, looming sphere filling the sky, visible in daylight, close enough to see atmospheric features. The gravitational effects of these close passes are significant. Each conjunction produces tidal forces that flex and squeeze both planets, generating internal heat and potentially triggering seismic or volcanic activity. It is not a gentle interaction. It is a periodic gravitational handshake that both planets feel in their cores. The system has been doing this for billions of years, and the fact that neither planet has been flung out of orbit yet is a testament to the precise resonance keeping them in check. But it is a precarious balance. One significant perturbation and the whole arrangement collapses. What makes Kepler 36 even stranger is the stark physical difference between the two planets. Kepler 36b is rocky and dense. Kepler 36c is gaseous and puffy. They orbit almost side by side, yet they are fundamentally different objects. In our solar system, rocky planets are in the inner region and gas giants are far out. Here, a rock and a gas ball are practically touching. The neat segregation we see in our own solar system is apparently not a universal rule. It is a local quirk. Most of the universe does not bother sorting its planets so tidily. Then there is Kepler 442b. This one hurts for a different reason, because on paper, Kepler 442b looks promising. It is a super-Earth about 1.3 times the diameter of our planet, orbiting in the habitable zone of a K-type orange dwarf star about 1,200 light-years away. Its equilibrium temperature is estimated around -4 degrees Fahrenheit, which is cold but manageable with a decent atmosphere and some greenhouse warming. If you were making a list of potentially habitable exoplanets, Kepler 442b would be near the top. And then you look at the star. K-type stars are generally considered good candidates for hosting habitable planets. They are dimmer and cooler than our sun, but they live longer and tend to be less volatile. The problem with Kepler 442 specifically is stellar activity. Observations have shown that the star produces flares, bursts of high-energy radiation that temporarily increase the star's brightness and bombard any nearby planets with ultraviolet and X-ray radiation. For a planet in the habitable zone, these flares could periodically strip atmospheric ozone, irradiate the surface, and sterilize any exposed biology. The flare problem is not unique to Kepler 442b. It is a recurring theme across hundreds of Kepler's habitable zone candidates. Many of them orbit small, cool stars precisely because those stars are the easiest to find planets around. But small, cool stars are also notoriously active, especially early in their lives. They flare frequently and violently, bathing their habitable zones in radiation that could prevent any atmosphere from surviving long enough for life to develop. The habitable zone, it turns out, is not always habitable. Sometimes it is just a kill zone with better marketing. Kepler also found systems that challenged our assumptions about what a solar system looks like. Kepler 11 has 6 confirmed planets, all orbiting closer to their star than Venus orbits our Sun's 6 worlds crammed into a space where we have one. Kepler 90 has 8 confirmed planets, matching our solar system's count, but the entire system is compressed into a volume smaller than Earth's orbit. It is like someone took our solar system and squeezed it until the planets were stacked on top of each other like coins in a roll. Kepler 47 was the first confirmed multi-planet circumbinary system, with planets orbiting a pair of stars. Kepler 16b, discovered earlier, had already proven that circumbinary planets exist, the real-life Tatooines. But Kepler 47 showed that entire planetary systems can form and survive in the gravitationally chaotic environment of a binary star. 2 stars orbiting each other while planets orbit both of them. The gravitational math is a headache. The fact that stable orbits exist at all is surprising. The fact that multiple stable orbits exist in the same system is borderline miraculous. The statistical legacy of Kepler is perhaps its most important contribution. Before Kepler, we knew exoplanets existed, but had no reliable way to estimate how common they were. After Kepler, we know the numbers are overwhelming. Roughly 20% of Sun-like stars host an Earth-sized planet in their habitable zone. That translates to at least 11 billion potentially habitable Earth-sized planets in the Milky Way alone. 11 billion. And that is just counting some like stars. Add in red dwarfs, which are far more numerous, and the number could be 40 billion or more. But here is the dark flip side of those numbers. For every potentially habitable world, Kepler found dozens that are definitively, catastrophically uninhabitable. Lava worlds, ultra-short period planets, bloated gas giants in impossible orbits, rocky worlds baked by flare stars, planets too hot, too cold, too irradiated, too unstable, or too bizarre to support anything resembling life as we know it. The galaxy is saturated with planets, but the overwhelming majority of them are hostile. The universe makes worlds with abandon. It makes livable worlds with extreme reluctance. Kepler ran out of fuel on October 30th, 2018, after 9.5 years in space. NASA officially retired the mission and put the spacecraft in a safe orbit around the Sun, where it will drift silently for centuries. Its data, however, is still being analyzed. New planets are still being pulled from the archives. Papers are still being published. The telescope is dead, but its discoveries continue, a ghost machine still revealing new nightmares from beyond the grave. Kepler changed everything, and what it changed our understanding into was considerably darker than what came before. Water is the most familiar substance on Earth. You drink it, you bathe in it, you swim in it. It falls from the sky, flows through rivers, and fills oceans that cover 71% of our planet's surface. Water is so integrated into a human experience that we use it as a baseline for everything. We measure temperature by when water freezes and boils. We define habitability by whether water can exist in liquid form. Water is life. Water is home. Water is safe, except when it is not. And on some planets, water becomes something that would make a chemist weep. Gliese 436b was discovered in 2004, orbiting a red dwarf star about 33 light-years from Earth. It is roughly the size of Neptune, about 4 times Earth's diameter, with a mass of about 22 Earths. Its orbital period is 2.64 days, placing it close to its star. The surface temperature is estimated at around 820 degrees Fahrenheit. So far, this sounds like a fairly standard hot Neptune. Nothing too shocking by exoplanet standards. And then you learn about the ice. Because Gliese 436b is covered in ice. Burning hot ice. Ice at 820 degrees Fahrenheit. That sentence sounds like a contradiction. Ice at 820 degrees should not exist. On Earth, ice melts at 32 degrees Fahrenheit and water boils at 212 degrees. At 820 degrees, water should be a gas, a superheated steam that wants nothing to do with being solid. And at normal pressures, that is exactly what would happen. But Gliese 436b is not at normal pressure. The planet's immense gravity compresses its water layer under pressures so extreme that the water molecules are forced into a crystalline lattice regardless of the temperature. The pressure overrides the heat. The ice stays solid because it has no choice. The form of ice on Gliese 436b is called Ice X, or possibly Ice 7, depending on the specific pressure and temperature conditions in different layers. These are exotic phases of water ice that exist only under extreme pressures, typically millions of times Earth's atmospheric pressure. Ice 7 has a cubic crystal structure completely different from the hexagonal ice we know. It is denser, harder, and can remain stable at temperatures that would vaporize normal ice instantly. It is, in every meaningful sense, a completely different material from the ice in your freezer. Same molecule, different universe. The structure of Gliese 436b, as modeled by planetary scientists, is layered like a nightmarish onion. At the center, a rocky and metallic core. Above that, a thick mantle of high-pressure exotic ices, burning hot but held solid by gravitational compression. Above that, a thinner layer where conditions might allow liquid water or supercritical fluid. And above that, a hydrogen and helium envelope that forms the planet's outer atmosphere. The surface, if you can call it that, is a transition zone where exotic ice meets superheated fluid meets pressurized gas. There's no line you could draw and say, here is where the planet starts. Gliese 436b also has a fascinating atmospheric quirk. Despite being a hot planet close to its star, its atmosphere contains very little methane, far less than models predict. Neptune, its closest solar system analog, has abundant atmospheric methane. Gliese 436b should too, given its temperature and composition. The methane deficiency remains unexplained. Something in the planet's chemistry is either destroying methane or preventing its formation. It is another small mystery stacked on top of the big one, another detail that does not fit neatly into our models. GJ1214b takes the water world concept in a different, but equally disturbing direction. Discovered in 2009 by the M-Earth Project, a survey that monitors small, nearby red dwarf stars for transiting planets. GJ1214b is a super-Earth about 2.7 times Earth's diameter and 6.5 times its mass. It orbits a dim red dwarf star just 48 light-years away. Early analyses of its mass and radius suggested a density consistent with a significant water content. This planet might be made substantially of water. Not just a surface ocean, water all the way down. If GJ1214b is indeed a water world, the implications are staggering. The ocean would not be a thin layer on top of a rocky surface like Earth's oceans. It would extend hundreds of miles deep, possibly thousands. At those depths, pressures would reach millions of atmospheres. And under those pressures, liquid water undergoes phase transitions into exotic forms of ice that have no analog in everyday experience. The bottom of GJ1214b's ocean might not be a rocky seafloor. It might be a layer of high-pressure ice, hot and dense, separating the liquid ocean above from the rocky core below. Imagine an ocean so deep that the water at the bottom has been compressed into solid ice by the sheer weight of the water above it. Not frozen by cold, frozen by pressure. This ice is hot. It sits at temperatures of hundreds or even thousands of degrees. Above it, a layer of supercritical water, a phase where liquid and gas become indistinguishable, where the fluid is simultaneously too hot to be liquid and too compressed to be gas. Above that, a potentially liquid water layer. Above that, a steam atmosphere. It is water in every possible state, stacked vertically, each layer stranger than the last. JWST observed GJ1214b in 2023, and the results added complexity without providing clarity. The atmosphere appears to be rich in heavier molecules, consistent with a water-rich composition, but high-altitude hazes or clouds obscure the deeper atmosphere, making definitive characterization difficult. The planet is keeping its secrets. We know it is there. We know it is dense enough to be water-rich. But the details of what that water world actually looks like beneath its hazy veil remain frustratingly out of reach. The most tantalizing water world in our neighborhood, and it wears a mask. The physics of water under extreme pressure is its own branch of science, and it has implications far beyond exoplanets. Laboratory experiments at facilities around the world have been compressing water to enormous pressures and discovering new ice phases with increasing regularity. Ice 7, Ice X, Ice 11, Ice 15, and most recently Ice 18, also known as superionic ice. Each phase has a different crystal structure, different properties, and different implications for planetary interiors. The simple molecule H2O, under enough pressure, becomes a material science playground. Superionic ice, Ice 18, deserves its own moment in the spotlight because it is one of the strangest materials in known physics. In superionic ice, the oxygen atoms are locked in a rigid crystal lattice, frozen solid, while the hydrogen atoms are free to flow through the lattice like a liquid. It is simultaneously solid and liquid. The oxygen is frozen. The hydrogen is flowing. And because hydrogen atoms carry electrical charge, superionic ice conducts electricity like a metal. It is ice that acts like a wire, frozen water that carries current. If you describe this to someone in the 19th century, they would have you committed. Scientists at Lawrence Livermore National Laboratory confirmed the existence of superionic ice in 2018 using laser-driven shock compression experiments. They blasted a thin film of water with lasers powerful enough to generate pressures of 100 to 400 gigapascals, millions of times atmospheric pressure, for a fraction of a second. In that brief window, they observed the characteristic signatures of superionic ice, the rigid oxygen lattice and the mobile hydrogen ions. It exists, it is real, and it almost certainly exists right now inside Uranus and Neptune, and probably inside many water-rich exoplanets. The presence of superionic ice in the interiors of ice giant planets could explain one of the longest-standing mysteries about Uranus and Neptune: their unusual magnetic fields. Both planets have magnetic fields that are tilted at extreme angles relative to their rotation axes and offset from their centers, unlike the relatively aligned fields of Earth, Jupiter, and Saturn. If a thick layer of electrically conducting superionic ice exists in their mantles, it could generate the kind of complex, asymmetric magnetic field we observe. The weirdest ice in physics might be the key to understanding the weirdest magnets in the solar system. Back to exoplanets, the broader category of water worlds, planets with substantial water content that is neither fully liquid nor fully ice in any familiar sense, may be one of the most common planet types in the galaxy. Analysis of Kepler data suggests that many super-Earths and many Neptunes fall in a density range consistent with significant water fractions. These worlds may represent a planetary class that has no analog in our solar system. Ocean planets with no seafloor, no continents, no land of any kind. Just water in various exotic states, all the way down to a rocky core buried under inconceivable pressure. The habitability implications of water worlds are sobering. On Earth, the interaction between water and rock drives geological cycles that regulate atmospheric chemistry. Volcanism releases carbon dioxide. Weathering of rocks removes it. This carbon cycle acts as a thermostat, keeping Earth's temperature within a range that supports liquid water. On a planet where the ocean is so deep that water and rock never interact, that thermostat is missing. The climate regulation that makes Earth habitable may depend on something as mundane as having a shallow enough ocean for rock and water to touch. Too much water might be just as deadly as too little. There is something almost philosophically cruel about that. Water is the molecule we search for on other worlds as a sign of potential life. Follow the water has been NASA's guiding mantra for decades. And now we are discovering that water, in sufficient quantity and under sufficient pressure, becomes something hostile, alien, and fundamentally incompatible with life as we know it. Too little water in a world is a barren desert. Too much, and it is a high-pressure nightmare of exotic ice and crushed fluid. Life needs water, but it needs exactly the right amount. The universe, as usual, is not interested in providing exactly the right amount. Let's talk about money for a second. Not the kind you have in your bank account. The kind that does not exist, could never exist, and would break the global economy so thoroughly that the concept of currency would dissolve on contact. Because somewhere out there, about 41 light years from Earth, there's a planet that was once estimated to be worth $26.9 million. That is a 26 followed by 30 zeros. For context, the entire GDP of planet Earth is about $100 trillion. This planet's estimated value is roughly 269 quintillion times the global economy. Its name is 55 Cancri E. 55 Cancri E was discovered in 2004 as part of a 5-planet system around 55 Cancri, a sun-like star visible to the naked eye in the constellation Cancer. The planet is a super-Earth, roughly twice Earth's diameter and about 8 times its mass. It orbits insanely close to its star, completing a full orbit every 17.7 hours. The dayside temperature reaches about 4,400 degrees Fahrenheit. By now, these numbers should feel familiar. What made 55 Cancri E different was not its orbit or its temperature. It was what scientists thought it was made of. In 2012, a team led by Nitku Midhusudhan at Yale University published a paper proposing that 55 Cancri E could be a carbon planet. Based on the measured mass and radius, combined with assumptions about the star's carbon-to-oxygen ratio, they suggested that a significant fraction of the planet's interior could be composed of carbon in its most compressed crystalline form, diamond. Not a thin layer of diamond, not diamond deposits. A planetary mantle made substantially of diamond, potentially a third of the planet's total mass. A diamond world. The media went appropriately insane. Diamond planet found. Planet worth $26.90, no million. The headlines wrote themselves. And to be fair, the science was plausible at the time. If a planet forms in an environment where carbon is more abundant than oxygen, the chemistry flips from what we see on Earth. Instead of silicates, the rocky minerals that make up Earth's crust and mantle, you get carbides. Silicon carbide, titanium carbide, and deep in the interior, where pressures are extreme, the carbon crystallizes into diamond. A planet built from fundamentally different chemical building blocks than our own. The reality, as it usually does, turned out to be more complicated. Subsequent studies revised the carbon-to-oxygen ratio of the host star downward, making a purely carbon-rich composition less likely. And observations by the Spitzer Space Telescope revealed that 55 Cancri E has dramatic temperature variations, with its dayside temperature fluctuating over time. These fluctuations suggested volcanic activity and possibly an atmosphere that comes and goes. The planet was not a static diamond. It was a dynamic, geologically active, utterly chaotic world where the diamond mantle hypothesis was just one of several possibilities. In 2024, JWST observations of 55 Cancri E delivered the most detailed picture yet. The telescope detected thermal emission from the planet consistent with a substantial atmosphere, possibly rich in carbon dioxide or carbon monoxide. The presence of a thick atmosphere on a planet this close to its star was itself surprising, as stellar radiation should strip it away. The implication is that volcanic outgassing is continuously replenishing the atmosphere, pumping gases from the interior to the surface faster than the star can remove them. 55 Cancri E is not dead. It is breathing, violently. Whether or not 55 Cancri E is truly a diamond planet remains an open question. The current data is consistent with multiple interior compositions, and pinning down the exact makeup requires measurements that are at the edge of current technology. But even if the diamond fraction is smaller than initially estimated, the planet almost certainly contains carbon compounds in exotic, high-pressure forms that do not exist naturally on Earth. It may not be a pure diamond world, but it is definitely not Kansas. If 55 Cancri E is the diamond planet we are not sure about, PSRJ 1719-1438b is the diamond planet we are quite sure about, and it is, by any measure, one of the strangest objects in the known universe. Discovered in 2011 by a team of Australian astronomers led by Matthew Bales, this planet orbits a millisecond pulsar, a neutron star spinning 174 times per second. The planet is roughly 5 times Earth's diameter, but far more massive, with a density so high that the only material consistent with its properties is crystalline carbon, diamond. But PSRJ 1719-1438b is not a planet in any normal sense. It is the remnant of a white dwarf star. Here is what happened. The system was originally a binary, 2 stars orbiting each other. One star died and became a neutron star. The other star was a white dwarf, a dense stellar corpse made largely of carbon and oxygen. Over billions of years, the neutron star's gravity stripped material from the white dwarf, transferring mass until the white dwarf shrank to a fraction of its former size. What remained was a planet-sized, ultra-dense ball of crystallized carbon orbiting the pulsar every 2.2 hours. A dead star compressed into a diamond. The object is about 60,000 kilometers in diameter, roughly 5 times the size of Earth, but it contains more mass than Jupiter. Its density is approximately 23 grams per cubic centimeter. For reference, lead has a density of 11.3, and osmium, the densest naturally occurring element on Earth, is 22.6. This planet is denser than osmium, denser than any bulk material that exists naturally on our planet. It is quite literally the densest ball of matter orbiting anything anywhere that we have measured. A diamond the size of a small gas giant. The philosophical question of whether PSRJ 1719-1438b is a planet at all is genuinely interesting. It was not born as a planet. It was born as a star, lived as a star, died as a white dwarf, and was then cannibalized down to a planet-sized remnant by a companion neutron star. At what point in that process does a stellar corpse become a planet? Is it about size, mass, origin, or is planet just a label we apply to anything that orbits something else and is not a star? The universe does not care about our categories. It produces objects. We struggle to name them. The broader theoretical class of carbon planets, sometimes called carbide planets or diamond planets, represents a fundamentally different kind of world from anything in our solar system. On Earth, oxygen is more abundant than carbon, so our rocks are made of silicates, minerals built on a framework of silicon and oxygen. On a carbon planet, the chemistry reverses. The rocks would be silicon carbide, titanium carbide, and iron carbide. The interior would contain layers of graphite and diamond. The surface, if cool enough, might be covered in tar like hydrocarbons and graphite dust. A dark, sooty, alien landscape. Carbon planets would have no water oceans. Water, H2O, requires oxygen, and on a carbon-rich world, most of the oxygen is locked up in carbon monoxide rather than water. No liquid water means no water cycle, no rainfall, no rivers, no erosion as we understand it. The geological processes would be entirely alien. Instead of plate tectonics driven by silicate mantle convection, a carbon planet might have a sluggish or immobile graphite crust over a diamond-rich mantle. The landscape would be static, dark, and dry. Beautiful in a stark, obsidian way, but utterly lifeless. How common are carbon planets? That depends on the carbon to oxygen ratio of the stars they form around, which varies across the galaxy. Stars in the inner regions of the Milky Way, closer to the galactic center, tend to have higher carbon to oxygen ratios. This suggests that carbon planets might be more common in the galactic interior. Our Sun, located in the galactic suburbs, has a relatively normal Kepler ratio that produces silicate planets. We may simply live in the wrong neighborhood to see diamond worlds, but in the crowded inner galaxy, they could be abundant. There is a bittersweet quality to the diamond planet story. Humanity has spent millennia valuing diamonds as the most precious of gemstones. Wars have been fought over them. Empires have been built on their trade. Engagement rings cost 3 months' salary because a marketing campaign in the 1930s said they should. And here, floating in space, are worlds made almost entirely of diamond, containing more of the stone than could ever be mined, processed, or sold. They're worth more money than has ever existed. And they're about as useful to us as a photograph of a sandwich is to a starving person. 55 Cancri E is 41 light years away. Even at the speed of light, a one-way trip would take 41 years. At the speed of our fastest spacecraft, it would take roughly 700,000 years. PSRJ 1719-1438b is about 4,000 light years away. We will never visit these worlds. We will never mine them. We will never bring back a single gram of their diamond interiors. They exist, glittering and unreachable, a cosmic joke about the gap between value and access. The most expensive objects in the known universe, and they might as well be imaginary. But perhaps the real value of the diamond planets is not monetary. It is conceptual. They prove that planetary composition is not a single recipe. Earth's geology is not the default. The silicon and oxygen framework that builds our rocks, our mountains, our continents is just one possibility on a menu of chemical outcomes. Change the starting ingredients, and you get entirely different worlds. Diamond worlds, carbide worlds, worlds where the ground is graphite and the mountains are industrial abrasive and the soil is hydrocarbon sludge. The universe is a chemistry set with no instruction manual and no safety warnings. And every single one of those chemical variations produces a world that would kill you. Not through malice, not through design, just through the cold arithmetic of physics operating on unfamiliar materials at extreme conditions. The diamond planets are not trying to hurt anyone. They are just being planets, following the same physical laws as Earth, but with different elements in different proportions. The horror is not that these worlds are hostile. The horror is that hostility is the default. Earth's gentleness is the anomaly, not the other way around. There's a point where a planet gets so hot that calling a planet starts to feel like a misclassification. Not because of any formal taxonomic rule, but because the conditions on the object have so thoroughly departed from anything we associate with the word planet that the label loses all meaning. KLT9b crosses that threshold with casual indifference. Discovered in 2017, KLT9b has a dayside temperature of 7,800 degrees Fahrenheit. To put that number in perspective, the surface of our sun is about 10,000 degrees Fahrenheit. KLT9b is nearly 80% as hot as the surface of a star. More relevantly, KLT9b is hotter than the majority of stars in the Milky Way. Most stars are red dwarfs and orange dwarfs with surface temperatures well below 7,800 degrees. KLT9b's dayside is hotter than roughly 80% of the stars in our galaxy. A planet hotter than most stars. That is not hyperbole. That is a measured, peer-reviewed, repeatedly confirmed fact. The object orbiting a star in the constellation Cygnus is, thermally speaking, more star than planet. The host star, KLT9, is an A-type blue-white star roughly 670 light-years from Earth. It is about twice as hot as our Sun, twice as massive, and significantly more luminous. KLT9b orbits this blazing star every 1.48 days, so close that it receives thousands of times more radiation than Earth receives from the Sun. The planet's orbit is also polar, meaning it passes over the star's poles rather than around its equator. This unusual geometry may be the result of gravitational scattering at some point in the system's chaotic history. At 7,800 degrees Fahrenheit, the chemistry of KLT9b's atmosphere enters a regime that borders on the absurd. Most molecules cannot survive. Hydrogen molecules, H2, which are the dominant component of gas giant atmospheres, are ripped apart into individual hydrogen atoms. Water molecules are destroyed. Carbon monoxide, one of the most resilient molecules in hot atmospheres, barely survives. The atmosphere is essentially a soup of individual atoms. Hydrogen, helium, iron, titanium, magnesium, sodium, all floating around as monatomic gases. It is not an atmosphere in any useful sense. It is a plasma with delusions of grandeur. In 2018 and 2019, multiple research teams detected iron and titanium in KLT9b's atmosphere using high-resolution spectroscopy. These detections were groundbreaking because iron and titanium had never been seen in a planetary atmosphere before. On Earth, these metals exist exclusively as solids or in industrial smelting furnaces. On KLT9b, they're gas, floating freely in the atmosphere at temperatures that would melt and vaporize them on contact. The periodic table on this planet is not a list of materials. It is an atmospheric weather report. KLT9b is also being destroyed. The intense ultraviolet radiation from its host star is driving a massive atmospheric escape. blowing off the outer layers of the planet at a rate that would strip away a significant fraction of its mass over the star's remaining lifetime. The star itself is evolving, getting hotter and larger as it approaches the end of its main sequence life. In a few 100 million years, KLT9 will expand into a subgiant and eventually engulf the planet entirely. KLT9b is racing between two deaths, being stripped to nothing or being swallowed whole. Neither outcome is pleasant. If KLT9b represents the extreme of temperature, TOI 849b represents the extreme of exposure. Discovered in 2020 by NASA's TESS mission, TOI 849b is approximately 39 times Earth's mass and about 3.4 times Earth's radius. Based on those numbers, its density is roughly equivalent to Earth's. But here's the strange part. A planet of 39 Earth masses should be a gas giant. At that mass, models predict that a planet would have accumulated a massive hydrogen and helium envelope during formation, becoming something like Neptune or Saturn. TOI 849b has almost no atmosphere at all. It is a naked core. The leading explanation is that TOI 849b is the core of a gas giant that lost its atmosphere. Either it was stripped by extreme stellar radiation, or it formed near other massive planets that disrupted its gas accumulation, or it suffered a catastrophic collision that blew its envelope off. Whatever the cause, the result is a planet-sized ball of heavy elements, rock, metal, and ice, baking at about 2,700 degrees Fahrenheit with no atmospheric blanket. It is an exposed planetary skeleton, a gas giant without the gas, like finding a skeleton walking around without skin, muscle, or organs, and being told it used to be a person. TOI 849b sits in a region of the mass-radius diagram called the Neptunian Desert, a zone where very few planets have been found. Planets in this mass range, orbiting this close to their stars, are expected to either retain their gas envelopes and become hot Neptunes, or lose them entirely and become bare cores. The desert exists because the stripping process is efficient. Most planets in this zone do not last long enough with their atmospheres intact to be easily detected. TOI 849b is a rare survivor, a core caught in the act of being naked, a specimen from a usually invisible population. Studying TOI 849b's composition could teach us what gas giant cores are actually made of, a question that has been theoretical until now. Jupiter's core is buried under thousands of miles of metallic hydrogen. We cannot directly observe it, but TOI 849b's core is right there, exposed, baking in starlight, available for spectroscopic analysis. If we can characterize its composition, we learn what Jupiter looks like under its clothing. TOI 849b is, in a sense, the only naked gas giant core we have ever found. It is exhibitionism in the service of science. And then there is Trace 2b, which might be the most aesthetically disturbing planet in the entire catalog. Discovered in 2006, Trace 2b is a hot Jupiter orbiting a star about 750 light-years from Earth. Its size and temperature are unremarkable by hot Jupiter standards. What is remarkable, unsettlingly remarkable, is its color, or rather, its complete lack of color. Trace 2b absorbs more than 99% of all light that hits it. It is measured by its geometric albedo, darker than coal, darker than black acrylic paint, darker than any naturally occurring substance on Earth. For comparison, coal reflects about 5% of light. Black paint reflects about 3 to 4%. Trace 2b reflects less than 1%. If you could somehow see it up close, and close enough that its own thermal glow was not visible, it would appear as a void. A sphere of darkness against the background of space, detectable only by the stars it blocked. A hole in the sky shaped like a planet. Scientists are still not entirely sure why it is so dark. Possible explanations include sodium, potassium, or titanium oxide absorbing visible light, but no model fully accounts for the extreme light absorption. Trace 2b is not entirely invisible, of course. At roughly 1,800 degrees Fahrenheit, it glows. The thermal radiation makes it emit a faint, deep red light, like an ember in a dying fire. So the true visual impression of Trace 2b would be a cold black sphere with a faint, bloody glow emanating from its heated surface. A dark world lit from within by its own torture. If you were designing a planet to be as cinematically evil as possible, you would end up with something very close to Trace 2b. The universe, apparently, has a flair for the dramatic. Together, KLT9b, TOI 849b, and Trace 2b represent three different ways a planet can reach the outer limits of what the word planet means. KLT9b is so hot it is functionally a low-grade star. TOI 849b has been stripped so completely it is barely more than an exposed boulder of heavy elements. Trace 2b absorbs so much light that it borders on being a hole in space. Each one of them forces us to ask, at what point does a planet stop being a planet and become something else entirely? The answer, inconveniently, is that there is no clean boundary. The universe builds objects on a continuum, and our categories are just lines we drew in the sand. These extremes also remind us how narrow Earth parameters really are. Our planet orbits at exactly the right distance to maintain liquid water. It has exactly the right mass to hold an atmosphere without crushing it. It absorbs and reflects just enough light to maintain a temperature range compatible with complex chemistry. It has a magnetic field that shields it from solar radiation. Every one of these parameters exists within a range that, when you look at the full spectrum of exoplanet extremes, is vanishingly small. Earth does not sit in the middle of the distribution. It sits in a tiny, improbable corner of it. The planets in this chapter exist at temperatures, densities, and albedos that would have been dismissed as impossible a generation ago. They are real, they are confirmed, and they are forcing planetary science to expand its definitions, revise its models, and accept that the universe's imagination exceeds our own by a margin so large it is almost embarrassing. We built our understanding of planets by studying 8 of them around one star. The universe has been building planets by the billions, around stars of every type, in conditions of every extreme. Our sample size was laughable, and now we are paying the price for that overconfidence. Everything we have discussed so far has one thing in common: a star. Every lava world, every glass-rained nightmare, every dying planet, an impossible survivor orbits something. They have a sun. They have an anchor. They belong to a system. But what about the planets that do not? What about the worlds that drift through the galaxy completely alone, with no star, no orbit, no light, and no destination? They're called rogue planets, and there might be more of them than there are stars. The idea of starless planets has been floating around astronomy since at least the 1990s. The basic concept is straightforward. During the chaotic early formation of a planetary system, gravitational interactions between forming planets can eject some of them from the system entirely. A close encounter between 2 massive protoplanets, or a gravitational slingshot from a passing star, can give a planet enough velocity to escape its host star's gravity forever. Once ejected, the planet becomes a free, floating body, drifting through interstellar space on a trajectory determined by its last gravitational interaction. In 2011, a landmark study using gravitational microlensing data from the MOA and OGLE surveys estimated that there could be roughly twice as many rogue planets as main sequence stars in the Milky Way. The Milky Way contains an estimated 200 to 400 billion stars. If the 2011 estimate is correct, that means there are 400 to 800 billion rogue planets in our galaxy alone. That is not a fringe estimate from a speculative paper. That was published in Nature, one of the most prestigious scientific journals on Earth. Hundreds of billions of dark, starless worlds. Subsequent studies have refined the numbers, and the picture is still staggering even with more conservative estimates. A 2017 analysis suggested the number might be lower than the initial 2011 figure, but still in the tens of billions. Other estimates have pushed higher, suggesting trillions if you include objects down to the mass of dwarf planets and large asteroids. The precise number depends on assumptions about ejection rates, formation environments, and the minimum mass you are willing to call a planet. But by any reasonable estimate, rogue planets are not rare. They are one of the most common classes of objects in the galaxy. Detecting rogue planets is extraordinarily difficult. They emit no reflected light because they have no star to reflect. They emit very little thermal radiation because most have cooled over billions of years to temperatures barely above the cosmic microwave background. They are dark, cold, and small by astronomical standards. Finding one is like looking for a black bowling ball in a dark warehouse the size of a continent. The primary detection method is gravitational microlensing. When a rogue planet passes between Earth and a distant background star, its gravity bends the star's light, causing a brief brightening that can last hours to days. Pulsar 2149-0403 was one of the first strong rogue planet candidates, identified in 2012 by a team using the Canada-France-Hawaii telescope. It is a young, relatively warm object, likely only about 50 to 120 million years old, with a temperature of roughly 750 degrees Fahrenheit. It was found moving through space in association with the AB Doradus moving group, a cluster of young stars. Its mass is estimated at 4 to 7 times Jupiter's mass, right at the boundary between a planet and a brown dwarf. The classification is debated, but it is alone. No star, no system, just drifting. In 2017, astronomers using the Korea Microlensing Telescope Network detected a rogue planet candidate through a microlensing event designated OGLE 2016 BLG 1928. The event lasted only 41 minutes, suggesting the lensing object was extremely small, possibly an Earth-mass rogue planet. 41 minutes. That is how long the universe gave us to notice this world existed before it vanished back into the darkness. A planet, possibly the mass of Earth, passing through a star's light like a ghost through a wall, visible for less than an hour, then gone forever. The most dramatic discovery came in 2021 when a team led by Nuria Moret-Roig published a study identifying at least 70 new rogue planet candidates in the Upper Scorpius and Ophiuchus star-forming regions, about 420 light-years from Earth. They used 20 years of archival data from multiple telescopes, looking for faint, red objects moving through the region without being gravitationally bound to any star. 70 rogue planets in a single modest patch of sky, not detected through microlensing, directly observed in infrared, young enough and warm enough to still glow with the residual heat of their formation. The 2021 discovery was important because it demonstrated that rogue planets are not just theoretical predictions from microlensing statistics. They are real, physical, observable objects that exist in significant numbers, even in a relatively small survey area. 70 rogue planets in one star-forming region. The Milky Way contains thousands of star-forming regions. The math scales up to genuinely uncomfortable numbers. We are surrounded. The space between stars is not empty. It is populated by wandering worlds we cannot see. What would a rogue planet look like? What would conditions be on a world cast adrift from its star? The answer depends on size, composition, and age. A large rogue planet, a gas giant ejected from its system in the last few 100 million years, might still retain significant internal heat. Its atmosphere would be frigid on the outside, but warmer deeper down. If it had moons, tidal heating might even maintain subsurface liquid water on those moons. A rogue planet is not necessarily a frozen wasteland. It could carry warmth and even chemistry within itself, like a dying ember drifting through the cold. A smaller rogue planet, a rocky world ejected early in its system's history, would have a grimmer fate. Without a star, the surface would cool to temperatures approaching absolute zero over billions of years. Any atmosphere would freeze and collapse onto the surface as ice. The world would become a dark, cold, airless sphere invisible to any telescope, drifting through the galaxy at speeds of tens of kilometers per second. No weather, no geology, no light, just a ball of frozen rock in perpetual, silent, lightless motion, forever. There is a theoretical possibility, proposed by physicist David Stevenson in 1999, that a sufficiently large rocky rogue planet with a thick hydrogen atmosphere could retain enough internal heat through radioactive decay and atmospheric insulating to maintain liquid water on its surface. No star required. The hydrogen atmosphere acts like a thick blanket, trapping heat from the planet's own interior. Under those specific conditions, a rogue planet could theoretically be habitable. Life on a world with no sun, no day, no seasons, lit only by the faint glow of volcanic vents and whatever bioluminescence evolution might produce. That scenario is speculative, but it is not impossible. And it raises the most disquieting version of the "are we alone" question that I have ever encountered. If life can exist on rogue planets, worlds with no star, no light, no connection to any stellar system, then life could be distributed throughout interstellar space in a way that is fundamentally undetectable. We search for life around stars because that is where we know how to look. But if billions of dark worlds drift through the galaxy, and even a tiny fraction of them harbor biology, then life could be literally everywhere, and we would have no way to know. Now for the question that keeps certain astronomers awake at night. Could a rogue planet pass through our own solar system? The answer is a deeply uncomfortable yes. The distances between stars are vast, averaging about 4 light years in our part of the galaxy. A rogue planet passing through would need to thread the needle between stars, and the chances of one passing close to our sun are small in any given century. But small is not zero, and over billions of years, the cumulative probability adds up. It has almost certainly happened before, and it will almost certainly happen again. In 2018, astronomers reported on Oumuamua, the first confirmed interstellar object to pass through our solar system. While Oumuamua was small, probably a few hundred meters across, its detection proved that objects from outside our system do enter our neighborhood. If small objects pass through, larger ones can too. A rogue planet entering the outer solar system would not necessarily cause immediate destruction, but its gravitational influence could perturb the orbits of outer solar system bodies, potentially sending comets and asteroids into the inner system. A visitor we never saw coming, causing damage we would not connect to its source. We would have almost no warning. Current telescopes can detect a rogue planet through microlensing only when it passes in front of a distant star from our perspective, an alignment that happens by chance and reveals the planet for hours at most before it vanishes again. A rogue planet approaching our solar system from interstellar space would be dark, cold, and essentially invisible until it got close enough for its gravitational effects to be measured. By then, it would already be inside our system. The burglar does not ring the doorbell. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will conduct a microlensing survey of the galactic bulge that is expected to detect hundreds of rogue planets, including potentially Earth-mass objects. This survey will give us the first statistically robust census of the rogue planet population. We will finally know, within reasonable error bars, how many dark worlds are wandering between the stars. The number is expected to be large, possibly very large. The galaxy's empty spaces may turn out to be not empty at all, but populated by invisible wanderers beyond counting. Rogue planets are perhaps the most existentially unsettling class of object in all of astronomy. Not because they are hot, or violent, or chemically extreme, but because they are invisible, because they are everywhere, because they move through the galaxy without allegiance to any star, on trajectories shaped by encounters that happened billions of years ago. Because the space between the stars, which we imagine as empty, is seeded with uncountable dark worlds drifting silently in every direction. We built our understanding of the cosmos around light. Rogue planets exist entirely outside that understanding. They are the universe's dark matter that we can, in principle, touch but never see coming. Saturn's rings, are one of the most iconic features in all of astronomy. Even people who know nothing about space can recognize them. Broad, flat, elegant bands of ice and rock orbiting the planet in a structure so photogenic it looks designed. Saturn's rings extend roughly 282,000 kilometers from the planet's center and are, in places, only about 10 meters thick. They are breathtakingly beautiful, cosmically significant, and absolutely puny compared to what orbits J1407b. J1407b, sometimes called Super Saturn, was identified in 2012 through unusual transit data observed by the SuperWASP survey. The host star, 1 SWASP J140747.93-394,542.6. Try saying that 5 times fast, showed a complex series of brightness dips over a 56-day period in 2007. Not the simple, clean dip of a planet crossing in front of star. A chaotic, multi-layered, multi-peaked dimming event that looked like something enormous and structured was passing between us and the star. Something with rings. Massive, complex, layered rings. Analysis by Matthew Kenworthy and Eric Mamajek in 2015 modeled the light curve and determined that J1407b has a ring system approximately 200 times the diameter of Saturn's. 200 times. If you replace Saturn's rings with J1407b's rings, they would extend further than the orbit of Mars. Seen from Earth, they would appear larger than the full moon in the sky. You would be able to see them with the naked eye. At sunset, you would look up and see a massive ring structure hanging in the sky, visible in daylight, dominating the heavens. That is how large these rings are. The ring system contains at least 30 individual rings separated by clearly defined gaps. Those gaps are significant. In Saturn's rings, gaps are carved by small moons whose gravity sweeps the ring material away. The gaps in J1407b's rings almost certainly indicate the same process. Moons are forming inside the ring system, clearing lanes as they orbit. We may be watching a miniature solar system in the process of being born. Moons coalescing from a disk of material around a planet, exactly the way planets coalesce from a disk around a star. Creation in real time. The total mass of J1407b's ring system is estimated at roughly 100 million trillion kilograms, about the mass of Earth. An entire Earth's worth of material spread out in a ring system 200 times wider than Saturn's. If you stood on one of J1407b's hypothetical moons and looked back at the planet, the rings would stretch across the sky from horizon to horizon, a shimmering, banded arch of dust, ice, and forming worlds. Every science fiction movie that has ever depicted a ring planet has been thinking too small. There is some debate about whether J1407b is a planet or a brown dwarf, a failed star. Its mass is estimated between 10 and 40 Jupiter masses, which puts it right at the ambiguous boundary. Brown dwarfs are objects too massive to be planets, but too small to sustain hydrogen fusion like a star. They're the cosmic equivalent of a teenager. Too big for the kids' table, too small for the adults. Regardless of classification, the ring system is real, it is enormous, and it is one of the most visually spectacular structures in all of exoplanet science. From megarings, let's move to double sunsets. Kepler 16b, discovered by the Kepler Space Telescope in 2011, is the first confirmed circumbinary planet, a world that orbits 2 stars instead of 1. The 2 stars in the Kepler 16 system orbit each other every 41 days, and the planet orbits both of them every 229 days at a distance of about 0.7 AU. From the surface of Kepler 16b, if you could stand on it, which you cannot because it is a cold gas giant, you would see 2 suns in the sky. 2 separate stars, rising and setting at different times, casting double shadows. The media immediately dubbed Kepler 16b the real Tatooine, after Luke Skywalker's home planet in Star Wars with its famous double sunset. The comparison is visually apt, but physically misleading. Kepler 16b is a Saturn-sized gas giant with a temperature around minus 100 degrees Fahrenheit. It is not a desert world with moisture farms. It is a cold, dark, gaseous sphere in an orbit that is gravitationally complex. The two stars in the system create a constantly shifting gravitational landscape that the planet must navigate, and the fact that it manages a stable orbit at all is a minor miracle of orbital mechanics. Circumbinary planets were long thought to be impossible. The gravitational interactions between two stars were assumed to be too chaotic for a planet to form or maintain a stable orbit. The math was messy, the simulations were discouraging, and then Kepler found one, and then another, and then another. Kepler 34b, Kepler 35b, Kepler 47's multi-planet circumbinary system. The universe was building stable planets around binary stars with a casual efficiency that made our theoretical objections look foolish. Not for the first time, not for the last. HR 8799, a young star about 129 light-years away, delivered one of the most stunning visual achievements in exoplanet science. In 2008, a team led by Christian Murwa used the Keck and Gemini telescopes in Hawaii to directly image for massive planets orbiting the star. Not detected through transits or radial velocity. Directly imaged, photographed, actual pictures of actual planets around another star. The four planets, HR 8799b, C, D, and E, are all several times Jupiter's mass, and they appear as tiny dots of light orbiting their star in a stately, multi-planet dance. The images are possible because HR 8799 is young, only about 30 million years old, and its planets are still radiating the heat of their formation. They glow in infrared, bright enough to be distinguished from the star's light using a technique called coronagraphy, which blocks the star's glare with a physical mask. Time-lapse compilations of HR 8799 observations, spanning over a decade, show the four planets actually moving in their orbits. You can watch alien worlds orbit an alien star. It is one of the most profound astronomical images ever captured, and it cost a fortune in telescope time. The HR 8799 system is also precariously balanced. The four massive planets orbit in near-resonance configurations that simulations suggest may be unstable over long timescales. The system might eventually tear itself apart through gravitational interactions, ejecting one or more planets into interstellar space or sending them crashing into each other. We may be seeing this system in a brief window of stability between chaotic formation and chaotic dissolution. A snapshot of order that will not last. Even the pretty picture has a dark timeline. Beyond these headline discoveries, Kepler and ground-based surveys found planetary systems with architectures that defy any pattern we could have predicted. HAT P7b, discussed earlier for its gemstone clouds, orbits in a retrograde or highly inclined orbit relative to its star spin. WASP 79b orbits on a polar trajectory, passing over its star's poles. GW Orionis hosts a planet-forming disk that is being warped and torn into multiple planes by the gravitational influence of three stars. Not two, three. A planet forming in that environment would see three suns in its sky, each pulling it in a different direction. Our own solar system, with its 8 planets orbiting in roughly the same plane, in the same direction, at well-separated distances, now looks almost suspiciously tidy, like a model apartment staged for an open house. Most real planetary systems, the data suggests, are messy, misaligned orbits, wildly different planet sizes crammed into small spaces, resonance chains that could collapse at any moment, binary and triple star hosts adding gravitational chaos. Our neat, orderly solar system is not the template the universe follows. It is the exception the universe occasionally permits. The diversity of planetary architectures tells us something important about the formation process. It is violent, stochastic, and path-dependent. Small differences in initial conditions, the mass of the protoplanetary disk, the timing of a nearby supernova, the gravitational influence of a passing star, can produce wildly different outcomes. Two identical gas clouds can collapse and produce solar systems that look nothing alike. There is no blueprint. There is no standard configuration. There is only the physics of gravity, pressure, and angular momentum, playing out differently every single time. J1407b's mega rings, Kepler 16b's double suns, HR 8799's glowing giants, and the zoo of exotic orbits found across the Kepler catalog paint a picture of a galaxy where every possible planetary configuration is tried, tested, and either sustained or destroyed. The successful ones survive. The failed ones are ejected, consumed, or torn apart. And the ones we observe are the survivors, the arrangements that happen to work, often barely, often temporarily. Our solar system survived, but there is nothing special about it except luck and timing. The next star over could host something completely, beautifully, terrifyingly different. February 22nd, 2017. NASA hold a press conference. The internet grinds to a halt. Major news outlets clear their schedules. The announcement is this: a team of astronomers has discovered 7 Earth-sized rocky planets orbiting a single star, and 3 of them sit in the habitable zone. 7 rocky worlds, 3 potentially habitable, all in one system. The star is called TRAPPIST-1. The headlines practically write themselves in neon. 7 new Earths found. Hope, after 20 years of exoplanet nightmares, finally had a postal address. TRAPPIST-1 is an ultra-cool red dwarf star about 40 light-years from Earth in the constellation Aquarius. It is tiny, about 9% the mass of our Sun, and only slightly larger than Jupiter in diameter. Its surface temperature is about 4,400 degrees Fahrenheit, compared to the Sun's 10,000 degrees. It is so dim that you cannot see it with the naked eye. The planets were initially detected by the Transiting Planets and Planetesimal Small Telescope, TRAPPIST, in Chile, and later confirmed and expanded by the Spitzer Space Telescope and ground-based follow-up. 7 worlds, all rocky, all roughly Earth-sized, all in tight orbits. The system is astonishingly compact. All 7 planets orbit closer to their star than Mercury orbits the Sun. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 days. The outermost confirmed planet, TRAPPIST-1h, takes about 19 days. If you place the entire TRAPPIST-1 system inside our solar system, all 7 planets would fit between the Sun and Mercury with room to spare. The planets are so close together that from the surface of one, you could see the others as clearly as we see the Moon, some even larger. It is a planetary system built to a miniature scale. Planets E, F, and G sit in the star's habitable zone, the region where liquid water could theoretically exist on the surface given the right atmospheric conditions. The masses and radii of all 7 planets suggest rocky compositions, with densities consistent with iron cores and silicate mantles, not unlike Earth. On paper, this was everything astronomers have been searching for. Rocky, Earth-sized planets at the right temperature around a nearby star. The scientific paper was published in Nature. It generated more media coverage than any exoplanet discovery before or since. People were naming their future colonies. And then, slowly, carefully, methodically, the actual science started deflating the balloon. The first problem was the star itself. TRAPPIST-1 is a red dwarf, and red dwarfs are angry little furnaces. They produce violent stellar flares, sudden eruptions of magnetic energy that blast X-rays and ultraviolet radiation into space. TRAPPIST-1 flares regularly. Some flares observed have been powerful enough to temporarily double the star's brightness in X-rays. For planets orbiting this closely, those flares are not distant inconveniences. They are direct hits. The radiation from these flares poses a direct threat to any atmosphere the planets might have. Ultraviolet and X-ray photons heat the upper atmosphere, giving gas molecules enough energy to escape into space. Over billions of years, repeated flaring can strip a planet's atmosphere entirely, leaving behind a bare, irradiated rock. Studies have estimated that the inner TRAPPIST-1 planets have likely lost multiple oceans' worth of water to stellar radiation over the system's roughly 7.6 billion-year lifetime. 7 billion years of being hit by a cosmic blowtorch tends to dry things out. The second problem is tidal locking. At the orbital distances of the TRAPPIST-1 planets, tidal interactions with the star are strong enough to lock each planet's rotation. So one side permanently faces the star and the other permanently faces away. The day side bakes in constant starlight. The night side freezes in permanent darkness. The terminator zone between the two experiences extreme temperature gradients and violent atmospheric circulation, if an atmosphere exists at all. Any liquid water would be confined to a narrow band at the terminator or pooled on the night side under a frozen cap. This is not the gentle habitability we imagined. The third problem is tidal heating. The TRAPPIST-1 planets orbit so close to each other that their mutual gravitational interactions create tidal stresses, the same mechanism that powers Io's volcanism in our solar system. Models suggest that the inner planets, TRAPPIST-1b and C in particular, could experience tidal heating intense enough to turn them into volcanic hellscapes. Not Earth-like, Io-like. Magma erupting through fractures in the crust, sulfur dioxide atmospheres. Surfaces resurfaced faster than they can cool. The habitable zone planets might escape the worst of this, but even they're not immune to the heating effects. Then JWST entered the conversation, and whatever hope remained took another hit. In 2023, JWST observations of TRAPPIST-1b, the innermost planet, showed thermal emission consistent with a bare rock surface and little to no atmosphere. The data indicated a dayside temperature of about 450 degrees Fahrenheit, which matches a dark, airless surface heated directly by starlight with no atmospheric redistribution of heat. No air, no greenhouse effect, no weather, just hot rock on one side and cold rock on the other. TRAPPIST-1b is not a second Earth. It is a barren, atmosphere-free stone. Follow-up JWST observations of TRAPPIST-1c, published in mid-2023, told a similar story. The thermal emission data was consistent with either a bare rocky surface or a very thin carbon dioxide atmosphere, no thicker than Mars's. Again, no substantial atmospheric blanket, no greenhouse warming, no protection from stellar radiation. 2 down, 5 to go. And while the habitable zone planets E, F, and G have not yet been fully characterized, the pattern is not encouraging. If the inner planets have been stripped bare, the outer ones face the same star, the same flares, the same relentless radiation. TRAPPIST-1 represents a broader and deeply uncomfortable pattern in exoplanet science. We find a planet that looks habitable. The media celebrates. The public hopes, and then detailed observations reveal that the planet is tidally locked, or flare-blasted, or atmosphere stripped, or volcanically active, or all four simultaneously. It happens again and again. Kepler 442b, Kepler 186f, Proxima Centauri b, LHS 1140b, each one greeted with optimism and then quietly downgraded as the data accumulates. The habitable zone is not a promise. It is a first date that almost never leads to a second. There are scientists who maintain cautious optimism about the outer TRAPPIST-1 planets. It is possible that planets E, F, or G have retained enough atmosphere, or replenished it through volcanic outgassing, to maintain surface conditions compatible with liquid water. Red dwarf stars, while flare-prone in their youth, tend to calm down as they age, and TRAPPIST-1 at 7.6 billion years old may be past its most violent phase. There's still a window for habitability, but it is a narrow window, getting narrower with each new observation, and the weight of evidence is not trending in the optimistic direction. The TRAPPIST-1 story is a microcosm of the entire exoplanet era's emotional arc excitement, tempered by data, eroded by reality. We wanted another Earth. We found 7 rocky planets at the right distance from their star, and even that was not enough. The star was wrong. The orbits were wrong. The radiation environment was wrong. The tidal forces were wrong. Everything that could undermine habitability was present, and everything that could support it was either absent or marginal. The universe gave us the architecture of hope and filled it with the furniture of despair. TRAPPIST-1 is still being studied. JWST will continue observing the system for years. Every transit of every planet is another opportunity to detect an atmosphere, measure a composition, or constrain a temperature. Science is not done with TRAPPIST-1, but the fairy tale version, the 7 New Earths headline, is finished. What remains is harder, more nuanced, and considerably less photogenic. 7 rocky worlds around a dim, violent star, probably stripped of their atmospheres, possibly volcanic, definitely hostile. Not a new home, a new lesson in how hard it is for the universe to make a place worth living. Of all the thousands of exoplanets discovered since 1992, one holds a special place in the human imagination simply because of its address. Proxima Centauri b, the closest known exoplanet to Earth, just 4.24 light-years away, orbiting the nearest star to our Sun. In cosmic terms, it is practically next door. You could fit the distance to Proxima Centauri between the Sun and the nearest other star with room left over for nothing, because that is the nearest other star. It is as close as exoplanets get, and it wants you dead. The discovery was announced in August 2016 by a team led by Guillaume Anglada-Escute, using radial velocity data from the European Southern Observatory. Proxima Centauri b is roughly 1.17 times Earth's mass, putting it squarely in the terrestrial planet range. It orbits in the habitable zone of its star, with an orbital period of 11.2 days and a distance of about 0.049 AU. At that distance, the planet receives about 65% of the radiation Earth gets from the Sun. On paper, conditions are right for liquid water. On paper, this could be it, the one we have been looking for. The announcement generated enormous public excitement, and understandably so. Here was an Earth-mass planet in the habitable zone of the nearest star. The Breakthrough Starshot initiative, funded by Yuri Milner, had already proposed sending tiny, laser-propelled probes to Proxima Centauri at 20% the speed of light, a journey that would take roughly 20 years. For the first time, a potentially habitable exoplanet was within conceivable reach of human technology. Not in our lifetimes, perhaps, but within a generation or two. The dream of visiting another world suddenly had a target. And then the problem started. Proxima Centauri is a red dwarf, like TRAPPIST-1, but closer and even more immediately relevant to our hopes. And like all red dwarfs, it flares. Violently, regularly, catastrophically. In 2018, astronomers observed a superflare from Proxima Centauri that increased the star's brightness by a factor of 1,000 in just 10 seconds. 1,000 times brighter in 10 seconds. The energy output of that single flare exceeded the largest solar flare ever observed from our Sun, and it was aimed directly at the habitable zone where Proxima b orbits. The radiation environment at Proxima b's orbital distance is extreme. Studies estimate that the planet receives X-ray fluxes roughly 400 times greater than Earth receives from the Sun. During flares, that number can spike by orders of magnitude. For any atmosphere the planet might have, these flares are devastating. UV and X-ray photons ionize atmospheric molecules, giving them enough energy to escape the planet's gravity. Over billions of years, this process could strip away an Earth-like atmosphere entirely. Models suggest that Proxima b has lost the equivalent of an entire ocean of water, possibly several, to stellar radiation over its lifetime. The planet is almost certainly tidally locked. At its orbital distance, tidal forces from Proxima Centauri would synchronize the planet's rotation with its orbit within a few 100 million years. One face always toward the star. One face always in darkness. The day side would be bathed in red dwarf starlight, dim and ruddy compared to our sun, but constant and unrelenting. The night side would freeze. Any atmosphere, if it exists, would have to circulate heat from day to night efficiently enough to prevent the night side gases from freezing and collapsing onto the surface. Most models suggest this is a close call at best. What would the surface of Proxima b actually look like? There are several scenarios, and none of them are inviting. In the best case, the planet retains a thick enough atmosphere to redistribute heat and maintain some liquid water near the terminator or in isolated regions. In this scenario, life is theoretically possible, but it would be under constant radiation bombardment, surviving in sheltered niches, never on the surface during a flare event. In the worst case, the atmosphere has been completely stripped, leaving a bare, irradiated rock that resembles Mercury more than Earth. Sterile, airless, dead. In 2020, a team announced the detection of a possible second planet in the Proxima Centauri system, Proxima c, a super-Earth roughly 7 times Earth's mass in a much wider orbit. If confirmed, Proxima c is far too cold for surface liquid water. It orbits at about 1.5 AU, but Proxima Centauri is so dim that at that distance, the planet receives about 3% of the light Earth gets from the sun. It is a frozen world in permanent shadow. The nearest multi-planet system to Earth may consist of a radiation-blasted wasteland and a frozen rock. Welcome to the neighborhood. Barnard Star, the second closest star system to the Sun at about 6 light years, had its own moment of planetary excitement. In 2018, a team announced the detection of Barnard Star B, a super-Earth roughly 3.2 times Earth's mass orbiting at the system's snowline. The planet, if real, would be too cold for surface liquid water with temperatures around minus 275 degrees Fahrenheit. But the detection was contested, and subsequent studies cast doubt on whether the signal was planetary or instrumental. As of the mid-2020s, Barnard Star B remains unconfirmed. Even the second nearest star system may be teasing us. Ross 128b, discovered in 2017, orbits a quiet red dwarf about 11 light-years from Earth. It is roughly Earth mass in the habitable zone, and its star is less flare-prone than Proxima Centauri. It is, by some metrics, a better habitability candidate than Proxima b. But even Ross 128b is tidally locked, poorly characterized, and too distant for detailed atmospheric study with current technology. It sits in a slightly less dangerous position on the same spectrum of red dwarf habitability challenges. A better hand, but still not a winning one. The story of our nearest exoplanet neighbors is a story of proximity without promise. The closest planets to Earth are all orbiting red dwarfs, because red dwarfs are the most common stars and therefore the most common nearby stars. But red dwarfs are hostile hosts. They flare. They lock their planets tidally. They irradiate their habitable zones. Every advantage that red dwarfs offer, their abundance, their longevity, their nearby examples, is offset by the violence of their relationship with their planets. Proximity is not the same as opportunity. The cruel irony is this: the nearest potentially habitable exoplanet orbiting a sun-like star, one that does not flare, is not tidally locked, and provides something resembling Earth's radiation environment, is much further away, probably tens or hundreds of light years, beyond the reach of any probe technology we can currently envision. The universe placed the right kind of planet around the wrong kind of star right next door, and the right kind of planet around the right kind of star just far enough away to be unreachable. It is almost like the cosmos is trolling us. Proxima Centauri b is still there, for 0.24 light-years away, still orbiting, still being blasted by flares, still, possibly, holding onto a thin, battered atmosphere, or, more likely, baking as a bare rock under a sky that occasionally brightens to 1,000 times its normal intensity. It is the closest other world we know of, and it is a monument to the gap between what we want the universe to be and what the universe actually is. The nearest door was always locked, and behind it, there was never a room worth entering. We have spent this entire documentary cataloging the horrors of planets we have found. Planets observed, confirmed, characterized, and nightmarish. But some of the most disturbing planets in our cosmic story are the ones that might exist but have not been found. The ghosts, the hypotheticals, the objects that leave fingerprints on the universe without ever showing their face. And the most famous of these ghosts lives, possibly, in our own solar system. Its name is Planet 9, and for a decade now, it has been driving astronomers slowly and methodically out of their minds. In January 2016, Caltech astronomers Konstantin Batygin and Mike Brown published a paper that sent the planetary science community into a frenzy. They had noticed that a group of distant trans-Neptunian objects, small icy bodies orbiting far beyond Neptune, had orbits that were suspiciously aligned. The orbits clustered together in a way that was statistically unlikely to be random. The probability of the alignment occurring by chance was estimated at about 0.007%. Something was hurting them. Something with significant gravitational influence. Something big. Batygin and Brown proposed that the alignment could be explained by a large, unseen planet in the outer solar system. Their models suggested a planet roughly 5 to 10 times Earth's mass, orbiting the Sun at an average distance of about 400 to 800 EU, on a highly elliptical orbit that takes between 10,000 and 20,000 years to complete. A super-Earth, lurking in the frozen dark, so far from the Sun that it receives almost no light and radiates almost no heat. Invisible to current surveys, present only in the gravitational shadows it casts on the objects around it. The search for Planet 9 has been ongoing since 2016, using some of the most powerful telescopes on Earth and in space. The challenge is immense. At 400 to 800 AU, Planet 9 would be thousands of times fainter than Neptune. It would move so slowly against the background stars that it could easily be mistaken for a distant galaxy or overlooked entirely in survey images. Finding it requires either a systematic sweep of an enormous area of sky or a lucky detection in archival data. As of the mid-2020s, it has not been found, but it has not been ruled out either. It might be there, it might not. Schrödinger's planet. The Planet 9 hypothesis has both fierce supporters and determined skeptics. Some researchers argue that the apparent clustering of trans-Neptunian object orbits is an observational bias, an artifact of where and when we have looked rather than a real physical grouping. Others have proposed alternative explanations. A primordial black hole, a disk of small icy bodies acting collectively, or simply statistical noise in a small sample size. The debate is ongoing and sometimes heated. Astronomers care deeply about whether there is a large planet hiding in our own solar system, and the uncertainty drives them to distraction. If Planet 9 exists, the implications are profound. It would mean that our understanding of the solar system is fundamentally incomplete. We have been studying this system for centuries. We have sent probes to every major body. We have mapped the asteroid belt, the Kuiper belt, and the scattered disk. And we missed a planet, not a small rock, a super-Earth, 5 to 10 times the mass of our world, hiding in the dark, silently shaping the orbits of distant icy bodies, patient and invisible. The idea that something that large could be that close and still undiscovered is, when you sit with it, genuinely unsettling. There are theories about how Planet 9 ended up in such a distant orbit if it exists. One possibility is that it formed closer to the Sun and was ejected outward by gravitational interactions with Jupiter and Saturn during the solar system's chaotic early history. Another possibility is that it was captured from another star during a close encounter billions of years ago, a stolen planet from a foreign solar system now orbiting our Sun at the edge of darkness. An alien world, in the most literal sense, that our Sun kidnapped and has been hiding ever since. From hypothetical present, let us travel to confirmed past. Thea. If Planet 9 is the ghost that might be here now, Thea is the ghost that was definitely here once. About 4.5 billion years ago, when the solar system was still young and violent, a Mars-sized body slammed into the proto-Earth at a speed of roughly 4 kilometers per second. The collision was oblique, a glancing blow rather than a head-on impact, and the energy released was so enormous that it liquefied both bodies, sprayed molten debris into orbit, and formed a disk of material that eventually coalesced into the moon. The giant impact hypothesis is the leading explanation for the moon's origin, and it is supported by multiple lines of evidence. The moon's composition is remarkably similar to Earth's mantle, consistent with being formed from the same material. The moon has a tiny iron core compared to its size, consistent with the impactor's iron core being absorbed by Earth. The angular momentum of the Earth-Moon system matches what you would expect from a giant oblique impact. Thea's fingerprints are everywhere. The planet itself is gone, absorbed into Earth and the Moon, but its legacy is literally hanging in our sky every night. Recent research has found possible remnants of Thea inside Earth itself. In 2023, a study published in Nature proposed that two massive, dense structures deep in Earth's mantle, called large low shear velocity provinces, located beneath Africa and the Pacific Ocean, could be chunks of Thea's mantle that sank into the Earth after the impact and have remained there for 4.5 billion years. These structures are continent-sized, denser than the surrounding mantle, and chemically distinct. If this interpretation is correct, pieces of an alien planet are literally embedded in the interior of our world. We are, in part, made of another planet. Thea is disturbing not because of what it is, but because of what it implies. Our moon, the most prominent object in our night sky, exists because a planet hit us. Our planet's axial tilt, which gives us seasons, was likely influenced by the impact. The iron core that generates our protective magnetic field was enhanced by absorbing Thea's core. The very conditions that make Earth habitable may depend on a catastrophic collision with another planet 4.5 billion years ago. We owe our existence to planetary violence. Life on Earth is the aftermath of a car crash. Then there is Nemesis, the darkest hypothesis of them all. In 1984, paleontologists David Ropp and Jack Sepkoski published a study suggesting that mass extinctions on Earth occur at regular intervals of roughly 26 million years. If true, the periodicity demanded an astronomical explanation. What celestial mechanism could cause periodic catastrophes on a 26 million year cycle? The answer, proposed independently by several teams, was Nemesis, a hypothetical red dwarf or brown dwarf companion star to our Sun, orbiting at roughly 1.5 light-years, periodically passing through the Oort cloud and sending a rain of comets into the inner solar system. If Nemesis existed, it would explain the apparent periodicity of mass extinctions by gravitationally perturbing Oort cloud comets on a regular schedule. Every 26 million years, Nemesis's orbit would bring it close enough to the Oort cloud to destabilize millions of cometary orbits, sending a barrage of impacts toward the inner solar system. Some of those comets would hit Earth. Some would cause mass extinctions. The dinosaurs might have been killed not by random chance, but by the clock-like gravitational influence of a dim stellar companion we have never seen. The Nemesis hypothesis has largely fallen out of favor. Infrared sky surveys like WISE have searched for dim stellar companions to the Sun and found nothing at the distances and masses predicted. The 26 million year extinction periodicity itself has been challenged by improved dating of geological boundaries. And the orbital mechanics of a companion at 1.5 light-years are precarious, likely to be disrupted by passing stars over billions of years. Nemesis probably does not exist, but probably is not certainly, and the hypothesis has never been formally, definitively, completely killed. It just slowly faded into improbability, like a ghost that everyone agrees is not real, but nobody is willing to say out loud. What connects Planet 9, Thea, and Nemesis is not their likelihood or their physical properties. It is the concept they embody. The universe can hide things. Enormous things, planet-sized things, right next to us. Our solar system, which we have studied for centuries with every instrument available, may still contain objects we have not found. Theia hid inside our planet. Nemesis hid in the dark. Planet 9, if it exists, hides in the cold reaches beyond Neptune. The most familiar region of space, our own cosmic backyard, is still full of secrets. And secrets that involve planet-sized objects are never comforting. The search continues. New telescopes, new surveys, new analysis techniques are deployed every year. The Vera Rubin Observatory, coming online in the coming years, will survey the entire southern sky repeatedly, potentially spotting slow-moving faint objects like Planet 9. Future infrared missions may find dim companions to nearby stars that previous surveys missed. And every improvement in geological dating narrows the window for or against extinction periodicity. The ghosts are being hunted, whether they are real or imaginary. The hunt itself tells us something important about human nature. We cannot stop looking, even when, especially when, what we might find disturbs us. Christmas Day, 2021. An Ariane 5 rocket lifts off from the European Space Agency's launch facility in Kourou, French Guiana, carrying the most expensive, most complex, and most anticipated scientific instrument ever built. The James Webb Space Telescope, 25 years in development, $10 billion, a sunshield the size of a tennis court, a primary mirror 6.5 meters across, made of 18 gold-coated hexagonal segments, folded like origami inside the rocket fairing. If any single component failed to deploy correctly during the first 2 weeks in space, the entire mission was dead. Nothing failed. Everything worked. And exoplanet science was about to be transformed. JWST operates in infrared, the portion of the electromagnetic spectrum associated with heat. This makes it ideally suited for studying exoplanet atmospheres, because molecules in an atmosphere absorb infrared light at specific wavelengths, leaving fingerprints that JWST can read with extraordinary precision. Where Hubble could detect a handful of atmospheric species in the best cases, JWST can characterize entire atmospheric compositions in a single observation. It turned transmission spectroscopy from a blunt tool into a surgical instrument. The results arrived fast. In July 2022, just months after reaching its operational orbit at the L2 Lagrange point, JWST observed WASP-39b, a puffy hot Jupiter about 700 light-years from Earth. The data contained the first unambiguous detection of carbon dioxide in an exoplanet atmosphere. Carbon dioxide, the same gas that regulates our climate, the same gas that drives the greenhouse effect on Venus, detected in the air of a world 700 light-years away. The spectrum was so clean, so definitive, that it felt like a proof of concept for everything JWST was designed to do. WASP-39b's full atmospheric breakdown, published shortly after, revealed a cocktail of molecules: water vapor, carbon dioxide, sodium, potassium, and even sulfur dioxide, a photochemical product created by starlight interacting with the atmosphere. The sulfur dioxide detection was particularly significant because it demonstrated that JWST could trace atmospheric chemistry in real time, not just detecting what is there, but understanding how it got there. The telescope was not just reading atmospheres. It was decoding the processes that shaped them, a level of detail that would have been science fiction 5 years earlier. Then came K2-18b, and the scientific community held its breath. K2-18b is a sub-Neptune planet about 120 light-years from Earth, 2.6 times Earth's radius, and 8.6 times its mass. It orbits in the habitable zone of a red dwarf star. In September 2023, JWST observed its atmosphere and detected methane and carbon dioxide. Both of these gases, together in a hydrogen-rich atmosphere, were unexpected. And then the team reported a tentative detection of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, specifically by marine phytoplankton. The dimethyl sulfide detection is tentative. It needs to be confirmed by additional observations. It could be a false positive from overlapping spectral features or an artifact of the data reduction. The scientific community has been appropriately cautious, emphasizing that the detection is preliminary and that non-biological explanations exist. But the mere possibility sent shockwaves through the field and the general public. A potential biosignature on a habitable zone planet, detected by a telescope from 120 light-years away. Even if it turns out to be wrong, it demonstrated that the tools exist to ask the question and get a meaningful answer. JWST has also been systematically working through the TRAPPIST-1 system, as we discussed, finding bare rocks where we hoped for living worlds. It has observed hot Jupiters, warm Neptunes, lava planets, and ultra-short period worlds, building the most detailed atmospheric catalog in history. Every observation refines our understanding of what exoplanets are actually like, not in theory, not in models, but in measured spectroscopic reality. And the reality, overwhelmingly, is hostile. JWST has confirmed, with unprecedented precision, that most planets are nightmares. But it has also shown that the chemistry of habitability exists on at least some worlds. The jury is out. The deliberation is ongoing. JWST is not the end of the story. It is the beginning of a new chapter. The European Space Agency's Plato mission, planned for launch in the coming years, will search for terrestrial planets in the habitable zones of sun-like stars. Not red dwarfs, sun-like stars. The kind of stars that do not flare, do not tidally lock their habitable zone planets, and provide a radiation environment similar to our own. Plato will observe up to 1 million stars and is expected to find thousands of new transiting planets, including potentially habitable world-around stars much more like our Sun. NASA's Nancy Grace Roman Space Telescope, also approaching launch, will conduct a massive microlensing survey of the galactic bulge, detecting thousands of exoplanets, including rogue planets, cold gas giants, and worlds in wide orbits that transit surveys miss. Roman will provide the most complete census of planetary architectures ever assembled, telling us not just what types of planets exist, but how they are distributed across the galaxy. It will complement JWST's atmospheric work with a population-level view. What does the full planetary landscape of the Milky Way actually look like? And further in the future, the Habitable Worlds Observatory, currently in development at NASA, aims to do something that no previous telescope has accomplished: directly image Earth-like planets around Sun-like stars and characterize their atmospheres for signs of life. Direct imaging, not transit spectroscopy, which requires a lucky orbital alignment. Not radial velocity, which tells you the planet exists but not what it looks like. Actual pictures, actuale spectra, of actual Earth analogs. If this telescope is built and launched, and if Earth-like planets around Sun-like stars have atmospheres with oxygen, water vapor, and ozone, we will see it. We will know. Within one generation, possibly within the lifetimes of people watching this documentary, we will have the technological capability to answer the most fundamental question human beings have ever asked. Are we alone? The tools are being built. The missions are being planned. The targets are being cataloged. The science is ready. The only question is what we will find. And both possible answers are, in their own way, equally terrifying. Scenario 1. We find life. We detect unambiguous biosignatures in the atmosphere of an Earth-like planet around a Sun-like star. Oxygen, ozone, methane, water vapor, in ratios that cannot be explained by geology alone. We confirm that biology exists elsewhere in the universe, that we are not alone, that life is a natural outcome of planetary chemistry, and it is happening right now on another world. The philosophical, religious, cultural, and psychological consequences of that discovery would be the most significant in the entire history of our species. Nothing would remain unchanged. Scenario 2. We do not find life. We point our most powerful telescopes at the most promising candidates, the Earth twins around Sun-like stars, the water worlds, the habitable zone rocky planets, and we find nothing. Sterile atmospheres, Dead chemistry. Worlds that have all the ingredients and none of the results. We survey hundreds of planets and find no biosignatures anywhere. The silence extends and deepens, and we are forced to confront the possibility that Earth is, against all statistical expectations, alone. That in a galaxy of hundreds of billions of planets, life happened exactly once. Here, that second scenario is, I would argue, the more disturbing one, because it means the universe is not just indifferent to life. It is almost perfectly hostile to it. It means the burning planets, the glass rain nightmares, the iron storm gas giants, the rogue worlds in the void, the lava oceans and diamond mantles and sulfuric acid clouds are not exceptions. They're the rule. And Earth, this fragile, improbable, preposterously specific arrangement of rock and water and air and magnetic field, is the exception. A fluke so rare it might as well be a miracle. One green in an ocean of fire and ice and darkness. Over the course of this documentary, we have traveled from the Mesopotamian desert to the cutting edge of space science. We have watched Giordano Bruno burn for imagining other worlds, and then found those worlds, and they were worse than even his persecutors could have imagined. We have cataloged lava oceans and glass rain and diamond planets and rogue worlds and dying gas giants and zombie planets orbiting the corpses of dead stars. We have found over 5,500 confirmed exoplanets as of the mid-2020s, and the vast, overwhelming majority of them are hostile to life in ways that make Venus look like a spa. The universe is not what we hoped it would be. It is not full of gentle, blue, water-covered worlds waiting for us to visit. It is full of violence, of extremes, of conditions so far outside human experience that we can barely describe them without resorting to metaphor and incredulity. The most common planets in the galaxy are not Earth's. They are screaming hell's capes of one variety or another. The habitable zone is not a guarantee. It is barely even a suggestion. And the nearest planets to us are, almost without exception, trying to kill any life that dares to exist on their surfaces. But we keep looking. That is the thing about human beings. We keep looking. We burned a man for imagining other worlds, and then we spent 4 centuries building the instruments to prove he was right. We found a universe full of nightmares, and we built better telescopes. We discovered that the nearest planet wants us dead, and we started designing probes to visit it anyway. The universe is under no obligation to be welcoming, and we are under no obligation to stop exploring it. The horror and the wonder are the same impulse, viewed from different angles. Somewhere out there, right now, a planet is being torn apart by its star. Somewhere else, glass is falling sideways through a blue atmosphere at 7 times the speed of sound. On another world, iron rain is hammering a surface that has never seen sunlight. A rogue planet is drifting through interstellar space, cold and dark and invisible, carrying its secrets in silence. A diamond world is glittering uselessly in the radiation bath of a millisecond pulsar, and a tiny red dwarf star, 40 light years away, is blasting its 7 rocky planets with flares that strip away the possibility of life one molecule at a time. And here, on this small, blue, improbably hospitable rock orbiting an average yellow star in the quiet suburbs of the Milky Way, someone is watching this documentary and wondering if there is anything out there like us. The answer, so far, is we do not know, but we're about to find out. And whatever we discover, whether it is life among the stars or silence among the nightmares, it will be the most important answer our species has ever received. We were never supposed to look, but we did, and we cannot stop now.